So first, I'm just going to go for all the handouts. That's what he mostly tests on. So I feel like that's the best preparation. So using the node voltage method, find the voltage at the essential nodes in the circuit below. Okay, so for node voltage, what we know basically is we need to identify the essential nodes. An essential node, what we can recall is essential node equals a node where 3 or more components meet. And so the first step is to identify the essential node here. And so if we look at this point right here, the 3 ohm, the 2.5, and the 10 ohm meet at that point. That's 3 components. At this point, the 10, the 5, and the 7 ohm resistors meet at that point. That's another essential node. And then if we, looking here, that's only 2 with the 25 volt and 3 ohms. It's not an essential node. It's only where 2 elements meet. But down here, we can see the 2 ohm, the 2.5 ohm, 5 ohm, and 3 amp current source. They all connect right here. So the node with the most components we create as our reference ground. And we're going to have to use the node voltage method for this. And so when we use the node voltage method, that's going to require us to create equations. And so we're going to start out by labeling our essential nodes. So I'm going to label this one V1 here and V2 here. And so we got our essential nodes labeled. We made our reference ground. The reference ground was where the most elements were for one node. So that's why we chose it for this one, since it's connected to 4 elements. And now we're going to create our equations. So let's start with V1. So what I like to do is I like to create an equation for V1 here. And so V1, we're going to do Kirchhoff's current law. So all the currents going out is equal to the current coming in. So we're just going to draw arrows going out. And so for our first one here, let's look at this left arrow, the arrow going to the left for the 3 ohm resistor. So we see this 25 volt source. And we know that source is going to give a current in this direction. So it's going in the opposite direction. So when I write the equation here for V1, where it starts at this point for this arrow, it's going to be minus 25 volts because that's in the opposite direction where the current flow is going for that source. So that's why the negative's in front of it. All over, there's 3 ohms in between. And so voltage divided by resistance is going to give us current. So now we solve for the current going out of this direction for V1. And now we're going to do an equation for the current going down from V1. And so I'm going to say plus the voltage at that node. And then there's no source. It's just connected to ground here. That's the path down here. So it'd be V1 minus 0 volts. So I'm just going to leave that as V1 divided by 2.5 ohms. And then after that, I'm going to write the third equation, which would be this arrow here to the right. And that would be V1 minus the voltage at the next node, which would be V2 all over 10 ohms. So plus V1 minus V2 all over 10. And now that we got those, we notice the current coming out is equal to the current coming in. And so since we have everything going out, the current coming in is 0. So we're going to say equal to 0 here. And now that we got the equation for V1, we have to find an equation for V2 here. And so let me do another one and draw out for you guys. And so for V2, what we have here is we're going to have an arrow going to the left, and then an arrow going down, and then an arrow going to the right here. So we're going to have V2, and then for this left arrow, minus V1 over 10. So for my equation for V2, we're going to have V2 minus V1, and then divided by 10 ohms. And then for the next one, we're going to have actually going this down arrow, V2 minus 0 because it goes to reference all over 5. So V2 minus 0, I'm just going to say V2 all over 5 ohms. And then for my third one here, it's V2, but we see there's not a voltage at the other side. We have this current source. So that current going through this arrow, it must be equal to the current going through the source, because it would be the exact same, whatever comes in must come out. So if there's this current going in, it must be equal to the current coming out, which is 3 amps. So I'm just going to write plus 3 amps because it's in the same direction. So that's why we have a positive. And now we're going to set that equal to the current that must go in must come out. And so we're going to have 0 amps going in because all of our arrows are drawn going out. And so now that we got the 2 equations here, what we need to do, I noticed I made 1 error. And so you guys pick up on this error because it's pretty significant and I didn't know if anyone was going to catch it. But
yeah, the 3 plus 2, isn't it?
Yes, good job, Fernando. 3 plus 2. And so you need to add here a plus 2 ohms. And it's because it's in the same branch we have here. And so the 3 plus 2, that's what you need. So you are using that component because the current does have to go through that resistor as well for this branch. And so now that we've got our equations all made, we're going to have to put our V1s together, our V2s together, and then form a matrix to solve. And so I'm going to combine like terms, so simplify. That's what we need to do here. So simplify these equations. And if we group it together for the first equation, so I'm going to write for the V1 equation, we're going to have, we have 1 over 5 for V1 here, plus 1 over 2.5, and then plus 1 over 10. When I do that, 1 divided by 5 plus 1 divided by 2.5 plus 1 divided by 10, I get 0.7. So I'm going to get 0.7 V1. And then for V2, I get negative 1/10, so negative 0.1 V2. And then I'm going to set that equal to, and then that would be negative 25 over 5 here. Add that to the other side. It's equal to 5. And so then once we got that value here, now we need to simplify the second equation here. So for the V1s, we have negative 1/10. And so I'm going to put negative 0.1 V1. And then for the V2s, we got 1/10 plus 1/5. When I do that, 1/10 plus 1/5, I get 0.3 V2. And then I'm going to set that equal to, and then move that 3 amps over to the other side, negative 3. And now what we need to do is we need to form the matrix. And so the matrix is going to have the coefficients in 1. So the coefficients in front of V1 is 0.7. And in the second equation was negative 0.1. And then the coefficients for the V2 was negative 0.1 and 0.3. And then after we find the coefficients, you're going to raise that to the negative 1. And then you're going to put your constants here in this 2x1 matrix. So 5 and negative 3. And then in your, you're going to set it equal to the unknowns. And this is what you need to type in your calculator. During the exam, he allows you to use your calculator. So this is the matrix you have to form on the left-hand side here. This is what you need to put in. And then that's going to give you the result in this form for V1 and V2. And so I have a special type of calculator, but if you don't have a calculator, I would pull up, in order to save yourself on the exam, just have the systems of linear equations calculator. And you can type it into it. Let me see if this one has.
Yo, Brian, before you continue, what happened to the 7 ohm resistor right next to V2?
V2.
Like, do we just not count it because there's no voltage source on the right side, or?
Okay, what happened was we had a current source in our node for voltage. When we're creating the node voltages. And so since we have a current source right here, what happens is we know the current source, what goes in must come out here. And so we must have 3 amps here. And so within this one part here, since we would be writing it in terms of current, because you can see when we write our equations, it's voltage divided by resistance. We have voltage divided by resistance. That means we're finding current for all these. So since we know the value of current, we just substitute it in instead of writing the V2 over minus 0 over 7, because that's going to create another unknown. We need to have our actual value for the current. And so since we know it's 3 amps, we can just plug that in directly.
Got you. So when it's a current source, act like there's no resistor there.
Yeah, got it.
But thank you.
Okay, now that we know that, let me, someone saying, looks like we got a chat here, and Fady, power sources govern the outcome of the node regardless of the resistors. Yes, correct, Fady, good job. Okay, now that we know that, that was a good question, Kato. I didn't understand that at all at first. So systems of linear equations calculator. And when you plug this in, let me see if there's a, I think I'd like this one. Okay, what you do is you just plug in the coefficients here. So my equation I had 0.7, negative 0.1, and then for my constant I had 5. And then here I got negative 0.1, 0.3, and then negative 3. When I just hit solve using the inverse matrix because that's what we do here. I get 6 and negative 8 here for my solutions. And so V1, that tells me it's equal to 6, and V2 is going to be equal to negative 8 volts. And so that's how I solve for V1 and V2. And to verify that against his, looks like he got, let me see, he did this matrix. Let me just check my answers because I checked these. Yeah, it's 6 and negative 8. I plugged it into a simulation. So mine are correct. He just didn't solve his. Okay, now we're going to go to number 2. And so for number 2, label the mesh currents in the circuit below and write the equations for mesh currents. Do not solve the equations, just write them. Okay. So mesh currents is different from node voltages. And so what you do is you create a loop within it where no other smaller loops can be inside. So here I'm going to create I1, going to create I2 here, and then I3 down here. And let me see if I can. And so we create loops where there can be no other smaller loops inside. So what we notice in this circuit, which is important, is that we have a current source in between the two. And when we write for our mesh currents is sort of different. Remember how the node voltages, we would have like a voltage over like a resistance or something? Well, when you're writing these equations, I'll show you guys, it's going to produce a different result. So let me start with this I3 just to show you guys what happens. So when you start with the I3, it's basically the voltages this time you're going to be finding. So you're going to have the 7 ohms times the current going to the right, which is I3, minus the current going to the left, which is I1 here. Because if we're following along loop 3, we're going in the direction of the current. So 7 times I3 minus I1. So that's what we're going to have for our first one here. So 7 ohms times I3 minus I1, and then plus the next one here is this 9 ohm resistor, and the current for the loop we're interested in is I3 minus the current in the opposite direction is I2. And so let me multiply that by that resistance value, 9 ohms. And then for our third equation here, we're going to have I3 times the 5 ohm, and there's no other mesh current that is affecting that one. So it's just going to be plus I3 times the resistance value, which is 5 ohms, and then set that equal to, and for value, it's going to be set equal to 0.
Đang học nè má. Đang học nè.
Oh, Tuan, I think you're accidentally not muted. Okay, cool. Now we're gonna form a mesh current equation, and we're gonna look at I1 and I2 here. And the important part, what we're going to see is we're gonna have to create a super mesh here. And for our super mesh, the reason we have to do that is that there's a current source between the two meshes, and that's a special equation we'll have to memorize. So let me just, okay. I need to make a note of it. For a super mesh, there is a current source between two nodes, but for a super node, there is a voltage source between two essential nodes. And so this is a big idea you guys are going to have to know, is a super mesh, there's a current source between two nodes, between two meshes. And so what we see in this problem here is he wanted us to realize that this was a super mesh here, because see this current source, it's between mesh I1 and I2. So we have to make a super mesh here. So that's what we're going to have to do. In the example above, if he wanted us to solve it using the node voltage method, if there was a voltage source between two essential nodes here, so let me say it's like right in here, that's when we're going to have to make a super node. And then this super node here would just be this one, and it would look something like this. It's arrows going out from it, because it would be in this direction. You sort of just treat it as one big node and just add these two. And you'd only have V1 here, not V2. And so what we have in this example is a super mesh, because there's a current source between two meshes. And so we're going to have to form one big mesh here. And so it's going to look like this. And I'm just going to call this big mesh here I1 plus I2. It just makes sense based off the drawing I have. And for that equation, let's write it out and see what it's going to be. So we see it's going to have 4 ohms, and this 4 ohm resistor, what's going to happen is that's going to be multiplied by I1. So let me write it, 4 ohm I1, and then plus this 6 ohm times I2. And then we have a 25 volt source here going in the opposite direction, the current, because it's coming out of the positive terminal. So it's in the opposite direction of the loop we drew, which starts at the 4 ohm and goes all around to the 2 ohm. So it's going to be minus 25 volts. And then plus this 9 ohm resistor down here. And for that 9 ohm resistor, the current from I2 is going in the direction we want, but the current from I3 is going in the opposite direction. So it's going to be I2 minus I3. And then plus the 7 ohm, which is I1 going in the direction of the loop we drew, and then minus I3, which goes in the opposite direction. And then plus 2 times I1, and then plus 20, because that goes in the direction that our loop is drawn. The currents coming out of that source is out the positive terminal in the same direction as the loop. And so we're going to set that equal to 0 here. And so we got one big equation, you can tell. And then for the I3, we got another equation. So now we're going to simplify. And so
Yo, my bad, Brian. I remember the professor telling us, let's say for I1, you see that 20 volt voltage source?
Yes.
Because it's going directly into the negative terminal first, we do minus 20. And then for the 25, we do plus 25. Or did I get that confused?
Okay, you're thinking of power, because power, the voltage drop. If the current goes from a positive to negative terminal, it's positive power. Because it goes down a voltage drop. But if the current goes from a negative to positive, it's a voltage rise. And so then that would be negative power. And so this is a different application where we're doing mesh currents. And so you know how I drew this loop right through here? Let me show you guys to make this super mesh. so it goes in this direction, okay? And from our sources, we know the current is coming out in this direction, so it's going in the same direction as the loop, but this current coming out of this one's going in the opposite direction. So that's why we give this a negative 25, but then for the 20 volt that goes in the same direction, we have a positive. Does that make sense?
That makes sense. Yeah.
Okay, cool. And then, so let's simplify this. So let me simplify going from the I1 and I2. So I'm going to collect all the terms together in that big equation. So the I1 plus I2, what we're going to have for that one is it's going to be, we have 4 plus 7 plus 2. So I got 9 plus 4, that would be 13, I1. And then for I2, we're going to have, let's see, 6 plus 9 plus, looks like that's it. So 15 I2. And let's look at I3. Negative 9 minus 7, negative 16 then. Negative 16. And then ohms times I3. And then for the constant, which is the voltage to the other side, that would be negative 5 if we combine them, and then to the other side, 5 volts. Okay, let's do the big equation, which is I3. And so, sorry, the smaller one, the loop. So negative 7, I get, so negative 7 times I1, and then for I2, it's going to be negative 9. So then for I3, it's going to be 7 plus 9, which is 16, and then plus 5, which would be 21. And then I3. And then let's see, are there any, we don't have any constants, that's going to be set equal to 0 here. And so now that we've done that, we're going to have to make a matrix out of this, or you can just solve it using the calculator I provided. And so I'm going to, oh, shoot.
My bad. One last question.
Yeah.
Did you not have to do I2 minus I1 equals 2 for the middle?
Oh, let me check. Oh, yeah, you're right. Good job for catching that. So basically, what happens is when we have these special conditions here, we do have to write a third equation. So you caught me right in the middle, right before. So see, everyone, how we have 3 unknowns here. We have 3 unknowns here, but we only have 2 equations. We need 3 unknowns and we need 3 equations. So you brought up a good point. We need to write a third equation here because we can't solve this. And so our third equation, everyone sees this 2 amp right here. Remember, we had our I1 here and we had our I2 here. And so our I1 and I2, if we look at that 2 amp current source going up, that's going to be, if we make one equation, the I2's in the same direction, but the I1's in the opposite direction. So what I'm going to write for this is I'm going to say the 2 amp source is going to be equal to the I2 minus the I1. And so right here, I2 minus I1. And I'm going to use that for my third equation down here. So I'm just going to have I1 with a negative coefficient in front, and then plus I2, and then set that equal to 2. And that's our third equation. And so now we can plug that in, knowing all those, into our equation here. So when
Brian, sorry, are you sure it's minus 25 and plus 20? Because the way I did plus 25 and minus 20. And when I just right now checked the professor's solutions, it is plus 25 and minus 20. I thought maybe if you flip the whole polarity thing, but our polarity matches up. Like all the pluses and minuses, they match up, except these 2. So I'm not sure what's going on.
Plus 25. Does he form a super mesh in the opposite? Because in my calculator, what I have here, I'm saying negative 20 volts. Did he make one? Same direction, make a super mesh. Goes up. plus 24. Yeah. Okay, you're correct, everyone. Okay, so never mind. Switch those signs. You guys were correct on that. So this should be actually -5 here, and then because that would be a positive 25, -20. Erase what I told you. So that'd be positive 5, and then move that to the other side, -5. And so then let's plug those in, see what we get here, and then check that against his. So for first one, we're going to get 13. For next one, we're going to get 15. And then here we're going to get -16. And then here we're going to get -5. Here we're going to get -7, -9, 21. And then we're going to get 0. And then for a third one, we're going to get -1. And then we're going to get 1. And then we're going to get 2. And so we're going to solve using the inverse matrix. And let me see. Okay. Oh, wait, sorry. We just need to write the equations. So that's what he wanted here. So for this one, if we match up, we have the 13, 15, -16, -5, 1. So let's see, 1, -1, 0, -3, 7, -7, -9, 21, and then 0. And then this one, he had opposite where he had -1. Why did he do that in his? Mine, I had IB minus IA, which is I2 minus I1. I think he might have made an error here because in mine, I got 100 and I did I2 minus I1 because I2 goes in the same direction and then I1. So I'm thinking he should have flipped
Put
this.
-3 in there. He put -3 somehow. Like somehow he got -3 for I1 minus I2.
Oh, so he multiplied by, okay, he did the opposite where he multiplied by like a -1 for this whole equation here. And then randomly he got a 3 amps, which is wrong because it should be 2 amps. So he did that incorrectly. This should be -2. So do not trust what he says here because it's a 2 amp source. It's not a 3 amp source. So what you should get are these 3 equations over here on this side. And so those are your correct ones. And now after we talked about that, hopefully that makes sense. So he just accidentally had, it should be a -2 here, but you could have this all multiplied by -1 to get the opposite of what we have here. And so now that we went over that on the mesh currents, the big takeaway from this was just remember when you form a super mesh, there has to be a current source between the 2 nodes. And when you form a super node, there's a voltage source between the 2 nodes. So that would mean up here, we would form a super node if there's a voltage source between the 2. And here we form a super mesh because there is a current source between these 2 meshes right here. And so then when you do that, you'll notice you'll have to write a third equation to have this source here or this source here, because you need the amount of equations for the amount of unknowns to match up. So that's a good example for covering all those little tidbits we might have forgot about. And so for this one here, number 3, it says find the Norton equivalent circuit. So when I see Norton equivalent, at first I think like Thevenin and then just convert to Norton, knowing our conversion equations. And so when I see this, the first thing I do is we have no dependent sources. So this is your go-to. So we have no dependent sources right now. And so you're going to use source transformation to find V Thevenin and R Thevenin. And what you do is you ignore the resistors in series with current sources and resistors in parallel with voltage sources. And so you make the combinations until there's only one source and one resistor. And so that might be a lot of wording. So if we go through an example here, how are we going to find the Norton equivalent? So we just got independent sources right here. And so we have no dependent sources, so we can use source transformation. That's our check. Do we have any dependent sources? If not, use source transformation. So that's why he says here you can use it. So what we're going to do is we're going to combine from the rightmost to the left because we want to go the farthest away from this open circuit here, these terminals. So we're going to start over on this side and simplify and go to the left. Okay, so we have a voltage source and we have a series resistor. And so what I see here is we have another series, we have a parallel resistor, and then we have this current source. So what I'm going to want to do is I'm going to want to create a conversion. So this 3 ohm becomes in parallel with this 4 ohm, and then I can combine them. And so what I'm going to do now is I'm going to create a current source. So 10 volts divided by 3, because V divided by R gives current. I get 3.33. And so I can redraw this section here as this 3 ohm resistor in parallel. And then we have this current source. That's 3.33. And you'll notice the direction is the exact same, the current coming out of the positive terminal. And so that's why I drew it in that direction. And then this resistor is 3 ohms, because it's in parallel. Now, since we did a source transformation, and now we have this 4 ohm resistor here. And we're going to do the parallel equivalent of those two. And so the parallel equivalent of 4 and 3, what you do is you do 4 times 3 divided by 4 plus 3. And I got 1.71 for this resistance value here. So 1.71. And then we still have our current source. And we have another current source right here, which is our 5 amps going downwards. So what we're going to do is you can combine the current sources in parallel, and you combine voltage sources in series. And so we have a 5 amps going down, and we have a 1.71 amps going up. And so we're going to combine it. So 1.71 minus that 5 amp, I get negative 3.28. So the equivalent source is going to be going downwards because it's negative, and then 3.28 amps. And then we're going to have that parallel resistor, and that parallel resistor is going to be 1.71 ohms. And then we're going to have our next one, which was this 7 ohm resistor here. And then we have our terminals A and B. And so with this 7 ohm, what we're going to have to do is we're going to have to convert this to a voltage source. So this resistor, this 1.71, becomes in series with this 7 ohm. And so when I convert that, 3.28 multiplied by the 3.28 multiplied by the 1.71 will give me the voltage equivalent. And so then I got this equivalent when I did I times R, that gave me voltage. So I got 5.61 volts. And then that 1.71 is now going to come up here, and it's going to be in series with that voltage source. And then we have these 2 other resistors here. And so I got this 7 ohm and I got this 1.71 ohm, and I can combine those two since they're in series. So 7 plus 1.71. And when I do that, I get 8.71. And so right here, I have 8.71, and then I have this voltage source here. And that's great and all. That would be my Thevenin equivalent, you guys, because I have a resistors in series with the voltage source here. And that is great, but it's asking for the Norden equivalent. And so that means that it wants a current source in parallel with a resistor. So we're going to have to do one last source transformation. And I'm just going to draw that up here. For last source transformation, I'm going to have to find that resistor value with that current source value. And so let me do that simple math. That resistor will stay the same value, so it's going to stay 8.71. And then to find the Norden equivalent, the current, so voltage divided by resistance, so 5.61 divided by 8.71. When I do that here, what I get is 0.644. So I'm going to write that here, 0.644. And let me see, milliamps. So that'd be milliamps. Let me check real quick to see, did I make any errors in here? So I got 1.67 here.
I think it's the 3.18. That's the error. No.
Looking at that, when I combined my 5 and then 1.71, see right here. Oh, how did I get 1.71 here?
It's supposed to be
Okay.
3.29.
Sorry, yeah, this should have been 3.33. I did the subtraction beforehand. And then minus this will give you right here. What's the value going to be is it's going to be 1.67. Good analysis, you guys, to see where the errors happen. And then right here, the equivalent would actually be 2.86 if we look at the source transformation. So that'd be 2.68 volts. And then that copies over right here. And then 2.86 divided by 8.71 here. When I do that, I get our value of 0.328 millivolts. So sorry, 0.328 volts, which is 328, 0.328 amps, which is 328 milliamps. And so right here, I'm just going to say 0.328 amps. So what we did to recap this problem is we started from the rightmost and went to the left. You start farthest away from the terminals. And what we did was a series of source transformations because we had no dependent sources. So you can ignore resistors in series with a current source, and you can ignore resistors in parallel with a voltage source. But here we have a series with a voltage source. And so we did a source transformation. So this 3 ohm would be in parallel with this 4 ohm. And then we found the equivalent resistance. And then after we found that, then we could combine these current sources since they're in parallel. We added those together. And then this 1.71 ohm resistor, we need to make it in series with the 7 ohm to combine it. So we did another source transformation to make this a voltage source in series with the resistor. And then we combined those two. And then it asked for a Norton equivalent. So we had to do our one last equivalent. So from the resistor in series, it became a resistor in parallel for a current source. And that's how we got this last answer of 0.328 amps in parallel with this 8.71 ohm resistor. And that's a recap of number 3. Okay, now that we did that, we're going to have to go to number 4, which is find the Thevenin equivalent with respect to terminals A and B in the circuit below. And so we are like, oh, is there any dependent sources? Yes, there is one, so you cannot do source transformation. Looking at his next step with dependent sources, you have to use node voltage or mesh current to find V Thevenin. And then you're going to deactivate the independent sources and redraw the circuit with a test voltage applied to those 2 terminals. And so let's use the node voltage method and let's try to find V Thevenin. So what I think of as V Thevenin is it's the node right before, see how the open circuit occurs here. It's this node right here. So the one right before that occurs. And the reason being is then this resistor then would be in series. And so then that would work out. And then we'd have our open right here. So what we need to do is we need to form, I'm going to say node voltage would be primarily the easiest here. Just for me, I find it easier than doing mesh currents. And so at this V Thevenin point, if we're going to see it's connected for other essential nodes, well, we have an essential node here, but we know it's at 20 volts. Down here, we have 3 components. So I'm going to just make this the ground node here. And then it looks like up here, if we're trying to see if there's any other, this V Thevenin, it's connected to all these as well. So when we have to work out that equation, it's going to be larger. So I'll call this V1 real quick for you guys. And let me walk you through how you're going to form all those equations because it can be a little weird at first. So V1 we know is at the potential 20 volts. And so that's super nice that we know that now. So it gives us a little easier time when we have to write the terms for V Thevenin. Let's write and see what we're going to get for other ones. So when I'm going to solve for this, what we need to do is we're going to have, let me do first the V Thevenin equation for that one here. And so our V Thevenin, what's going to happen is you notice there's one going down here and then one going to the left here. This is an open circuit, so no current's going to be supplied to it. This arrow going to the left, though, is going to have to branch off into 1, 2, and 3 directions, so we know. And so we're going to have to solve for that. And so when we write this, just to not confuse ourselves, we have to write 4 terms in that equation. And so let's start out for the V Thevenin. So V Thevenin minus 0 volts here divided by 2. So that's a simple one. V Thev divided by 2, because we'll just simplify V Thev minus 0 over 2. And then this arrow going down here, we notice there's a current provided. So it's going to be the current's going in the opposite direction of the arrow going out of V Thevenin. So it's going to be negative 5 amps here, minus 5 amps. And then what's going to happen here is we're going to have V Thevenin minus V1 over 10. And so plus V Thev minus, and then we know V1 is at a potential of 20 volts, like I told you guys. So we can just substitute in here 20 volts for V1. So we can say this is equal to 20 volts. So I'm just going to say minus, when we write it, V Thev minus 20 over, and then that resistor value is 10. And then up here we have our dependent source. And so what we're going to have to do is we notice this is a current source. So we can sort of treat it similar to an independent current source. What I'm going to do is that current source is going in the same direction as this arrow here going up. And so we're just going to add that 3 IA. And that's going to be set equal to 0. Because what's coming out of V Thevenin is going to be equal to what's coming in. None of our arrows go into V Thevenin. Now that we know V Thevenin's equation, we can see here we have, oh, what?
Quick question. So usually when I start any kind of circuit analysis, I start off from the far left. That's usually where most power sources are, and then that's how it goes. I've never seen, I've never even seen the professor do it. This looks like a really easy way, so I'm just curious. How do you know? How did you configure it that way? Because when I tried to solve this, I did it the regular way. I put V1 at the 5 amps, and then I said, okay, what's going in, what's leaving, and then I put V Thevenin at the where exactly you put it, but it's just
okay. I made that same error, Fady, and I was noticing in the textbook they made it simpler because look here, these are connected, right? So legit, this resistor, this 2 ohm is right here. If you sort of think of it, just pretend it's not here, and then see how it's connected to A here. They're all connected right there. So if you would, this goes down the 2 ohm resistor. So technically, this node for V Thevenin, you can draw it anywhere along that line because they're all connected. So I could draw it here. I could draw it here. It's the same exact point because it's all connected along this one branch here. And so you can draw that V Thevenin where you want to. And so I drew it over here to the right, just right before, because I always think of the voltage source with the series resistor for the Thevenin equivalent. And so I just drew it up there for a reminder myself.
I'm mainly concerned about the arrows, where the current is traveling.
So what I do is, let's say I create this node for V Thevenin. Okay, we know we need to draw arrows coming out of this point. So one's going up, one's going here to the left, one's going down, one's going to the right. This one going to the right, we have an open circuit here, so no current's going to flow through. So none is going to go through here, so I'm not going to show an arrow there. However, we're going to have a current go down here because there's a resistor and it is a closed circuit. So there's going to be current going down here. So that's going to represent our arrow going to the right here. So that's why I have 1, 2, 3, and 4. Does that make sense?
Yeah, I see. And the one that's going to the right, that's just technically going into the node if you put a negative value there, right? Because you have there's definitely current going into the node from the 20 volts.
Going into the node from the 20 volts. Oh, are you talking about going into this source down here?
Yeah, like after the source, and you see that one node V Thevenin that you labeled, there is current going up, there's current going down, but the current that's going to the left, whatever is coming from that's usually going into the node, not out of it. Do you see
Yeah,
what I'm
what
saying?
I think is I always draw it where it hits another voltage source. So it hits a voltage source here at this other node, V1. It's going to hit the ground. And then this one's going to hit this voltage source here at V1, the other node. And then it's going to hit here the ground. So whatever it hits first, that's what I just think of when writing my equations. So that's why when I drew the V Thevenin, I did V Thev divide by 2. That's the one right here. And then the -5 amps, one right down here, hit the ground, that other node. And then the VThev minus 20 divided by 10, it hit this other node here. And then the last one, 3IA, it hit the other node. And that's how we stop there. Does that make sense?
Yeah, that definitely
Okay.
does. Thank you.
And now that we covered that, how to write the equation for VThev, what we're going to do is we need to solve for VThev. So we have, look in this equation here, everyone. We have one unknown VThev and we have a second unknown IA. So let's write an equation for IA. Because if you remember up here in this example, we made an equation for the 2 amps. So we can make an equation here for the IA. If you think about it, because we have the voltage, VThev, and V1 on both sides, and we have a current. So voltage divided, and a resistance. Voltage divided by resistance gives us current. And so let's make an equation for IA. So an equation for IA, it's going to be V Thevenin, because where it starts out at and where it goes to. So V Thev minus V1 all over 10. So V Thev minus V1 all over 10. That's a very important concept you guys take down, is you can write an equation for the current when you have a dependent source, because it's going to be labeled somewhere else. So this is going to equal IA. And now that we know it's equal to IA, this up here, remember, I told you guys V1, sorry, is 20 volts. So I'm just going to substitute that in here and say for V1 here, it's actually 20. And now that we know that, we know the value of IA, so we can plug it in up here to this other equation. So for IA, let's plug it in there. So it's going to multiply everything through by 3. And so when I'm going to now rewrite this V Thevenin equation down here, and we're going to simplify that, and that should give us our value for the V Thev. And so let me rewrite this equation, make it logical. So we're going to have 0.5 V Thev, and then minus 5, and then plus, then we have 1/10, so 0.1 V Thev, and then here we're going to have minus 2, 20 divided by 10, then plus 3 times 0.1 VThev, so that'd be 0.3 VThev, and then 3 times negative 20 over 10, so that'd be -2, so -6, and then set that equal to 0. So that's what our equation. And now let's simplify it. So 0.5 plus 0.1, that's 0.6 plus 0.3, 0.9 VThev. And then minus 5, minus 2, -7, minus 6, -13, equal to 0. Okay, when I put this 0.9 VThev is equal to 13. Okay, let's solve this. And for my VThev value, when I do 13 divided by 0.9, I get 14.44. And that is going to be 14.44 volts. And now that I know the value of VThev, I need to find the value for RThev. And so remember, going back to his worksheet here, we found the node voltage. So we did all this. And so we did all of part A here to find the VThev. Now we have to deactivate the independent sources and redraw the circuit with a test voltage, and then find the current from the test voltage, and then solve for that, because R Thevenin is equal to the test voltage divided by the test current. This was a little tricky at first for me to understand, so I'm going to try and make this simple. So deactivate all independent sources. When you deactivate a voltage source, it becomes a short circuit here. So it's just going to look like this. And then when you deactivate a current source, it becomes an open circuit. So then this would not exist. There would be an open circuit here. And so you can draw it almost without that branch even existing here because it's all open. So this does not exist, this branch right here. And so I'm going to redraw that circuit to make it look better when you deactivate all those. And so I'll put that right here. What we have is we're going to have this 3IA. So let me draw that. The 3IA still. And then we're going to have this 10 ohm resistor. And we're going to have a short here at this 20 volt, an open circuit. So there's going to be no branch. Then we have this 2 ohm resistor right here. And then we're going to have terminals A and terminal B. Okay. Now that we know that, what we need to do is we're going to have our equation. So we need to apply a test voltage at this at this open circuit here between terminals A and B. And so we're going to have to apply that. So let me start drawing that out. Okay, so when we apply test voltage, it's going to look something like this. I'm going to do a different color. You're going to put a voltage source here. I just do the positive terminal up top and then negative, doesn't matter, whichever way you want. And then I'm going to call it VT for my test voltage. Current's going to be coming out of this test voltage. I'm going to call that IT. Okay, now that I drew that for you guys, if you sort of look at this circuit, it can be made a little simpler. If you notice, because this 3IA is in parallel with this 10 amp, and then those are in parallel with this 2 ohm here. So I can sort of just redraw this in general to just make it simpler for you guys so you can sort of see it. So this 3IA coming down here, and then this 10 ohm here. And then we have this 2 ohm in parallel with this. And then we have our test voltage over here. So our voltage from test. So now we're going to have to make our equations here. So VT for test voltage and our IT going here. And so if we want to make our equations, what we have to do is we know what's going to be happening. And so if we want to solve for this test voltage, think of the current going in is going to have to be equal to the current going basically out. And so if we look here, this test current coming in is going to be equal to the current going down here, and then the current going over here. And this current going to the left is going to be this current going down here and down here. That's the only two options it has. So that test voltage is going to be equal to the current going for the 2 amps plus the current going for the 10 ohm plus the current going for this 3 IA, which is that dependent source. And now we need to solve for that. So I'm going to write an equation. And so the test current is going to be equal to, and I'm going to look at this. And so it's in parallel, and we know a parallel circuit here, the voltage drop is the same. And so down this one, it would be, so going first for this one right here, this current going down here, VT divided by 2 amps, because the voltage drop across all these is going to be the same, and VT is in parallel. So we know the voltage drop across all these 3 components, the dependent source and these 2 resistors, is going to be VT. That's one fact we know about parallel circuits. Voltage drop is the same. So it's going to be VT all over 2 ohms here. And then for the next one, it's going to be VT over 10 ohms. And then for third one, it's going to be that dependent current source. So what we're going to do is we're just going to write, see how the current is going in the same direction as the dependent source. I'm going to write for this plus 3IA. And so I wrote an equation that tells you the current coming in is going to be equal to the current coming out. And so that's equal to the voltage drop across the component divided by the resistance of the component. And same with this 10 ohm resistor, the current going through it is going to equal the voltage drop divided by the 10 ohm resistor. And then the current going through here, it's going to be that current through that dependent source. So that's why I could just write it here, because it's a current source that tells you the current going through it. And so I wrote this equation right here. And we know that I of A, we can write an equation for that, because you look in this one down here and you're like, oh, great, I got one unknown here. I got another unknown right here. And I got a third unknown right here. What do I do? And so we can write an equation for 3IA. Remember how IA up here is across the 10 ohm resistor? So I of A right here, we wrote an equation for this actually, and it's VT over 10. So what you can do is you can just substitute that in for IA here. And so what we're going to get is we're actually going to get 3 times this plus this. So it's going to be 4 VT over 10 simplified. And then plus this VT over 2. And that's going to be
Quick
equal,
question.
yeah.
Oh, my bad. I know it's VT over 10, but why couldn't it be VT over 12?
Why couldn't it be VT over 12? Are you saying why didn't we add
The 2 ohms? Yeah.
because it's in parallel, so the voltage drop across here only corresponds to the 10 ohm resistor. The voltage drop across here only corresponds to the 2 ohm resistor here. And so we can't combine them because they're not in series, they're in parallel.
Got you. Okay, thank you.
Okay, and so that's why we can write this equation here. The current coming in is equal to the current going out. And then we know we can substitute in for I of A, because I of A was the current going across this 10 ohm resistor. And so the current we found right here going through, so we could simplify it to get this equation here. And so we have 1/2 VT plus 4/10. And so that'd be 5/10 plus 4/10, that's 9/10. So I'm going to say 0.9 VT here. And then that's going to be equal to our I of T. And now that I know I of T and I know VT, what I can do is I'm going to erase this upper part here because we found the Thevenin equivalent down there, that voltage, just because I'm running out of room. So now that we know this equation, it's pretty important because you're going to see our Thevenin is equal to the test voltage divided by the test current. And so it's going to be equal to VT over IT. We just solved for I of T, everyone. And so since we just solved for I of T, that means we can legit just plug in this 0.9 VT into here. So our R Thev becomes VT all over 0.9 VT. And when we do 1 divided by 0.9, because the VTs cancel in the numerator and denominator, what we're going to get is we get 1.1111. And so I just say 1.1 ohm as our R Thevenin value. And so since we know R Thev and V Thev, we can make the Thevenin equivalent circuit. And so our Thevenin equivalent circuit here, if we drew it out, since we know the Thevenin voltage and the Thevenin resistance, I'd have my voltage source here. So this would be the 14.44. And then I would have this current source, this resistance, which would be 14.44 volts. For VThev, this resistance, which would be 1.11 ohm. And then we would have our open circuit for these terminals A and B. Okay, now that we found all that, so this is what it would look like right here. So this is what he would want. You found the Thevenin equivalent and you found the R Thev value. So that's what you should receive. So quick summary, number 4, what we did is we couldn't use superposition. Sorry, not superposition. We couldn't use the first one of source transformation here because we had a dependent source in the circuit. And so what we did is we used the node voltage method. And so we found our node for V Thev. You can make it right here. So we found our V Thev. We used node voltage equations and we found the value of V Thev down here. And then we remove the independent sources. So voltage source becomes a short circuit and then current source becomes an open circuit. And so then we applied a test voltage at these terminals here. And so our test voltage went up here. So I'm just going to call this V of t. And we wrote an equation for the current going through all the elements. So I of t. And then we substituted into our equation here, the Thevenin resistance is equal to the V test divided by the current test. And then we plugged it in and we found our resistance Thevenin value, and we were able to create our simplified Thevenin circuit diagram. Okay, now that we went over number 4, let's do number 5. And so what we're going to get here for number 5, find the voltage at the essential nodes in the circuit below. And so my first course of action is like, oh my word, I see the circuit. What the freak do I do? So don't worry. What you're going to be like is I would be like, oh, right off the top, hey, this guy is in series. This 8 ohms in series with this 20 ohms. This 8 is in series with the 20. And look, this 2 is in series with the 6. So just simplify it like, whoa, 1, 2, 3, 4 simplifications. So this circuit's going to look something like this. So 1 up here, 1 down here. And right here. And okay, and so if we combine the 8 and 20 here, we're going to get a 28 ohm. If we combine the 5 and 9 up there, we're going to get a 14 ohm. If this one right here is just 20 ohm, sadly doesn't combine with anything. The 2 and 6 combine to make 8 ohm. And then here the 8 and 2 combine to make a 10 ohm. Okay. Now we know all those. This voltage source here is 6 volts. So I'm going to write 6 volts here and then negative and positive terminals. And then over here, this one is just 7 ohms. This voltage source stayed the same, so 5 volts. And then this current source over here is 4 amps. And so I'm going to use the node voltage method because it's easier than the mesh current. And so remember, if you are going to make a super node, the one thing you look out for is that, is there a voltage source between 2 essential nodes? And when I'm looking at this, I'm like, yeah, we're going to have 2 super nodes because look here, we have a voltage source here between, oh wait, no, we don't have it because that's a good thing to actually run into is see, it's not between the voltage source because our essential node here would be up here because 3 elements meet, another one right here, a third one right here, and then a 4th one down here. And this is connected to the most elements. So that's why I created ground. So this would be V1 here. This would be V2, V3. And if it was connected between the 2, it would actually be like here, the voltage source, but it's not. So it's not connected. But so we don't need to form any super nodes. However, we're going to have to solve this using the node voltage method. So we're going to have to create some of our equations. So for V1 here, what it's going to look like is our V1, it's going to be V1. What?
You just put
My
the
bad,
stuff in
Brian.
the shopping
I
cart.
was gonna ask you, why wouldn't you use mesh currents here? I know that node voltage is easier, but like, wouldn't it still be possible to use mesh currents?
Yeah, you can use mesh currents. The only reason I don't use mesh currents is because they get messy quick. And so I find node voltage easier for me personally because I don't get as confused. However, if one method is not working for you, do the other method and it might work simpler. It's just a matter of personal preference. And I find node voltage super easy because I don't like making super meshes. When that occurs, it makes it confusing to make a diagram. So I always say go to node voltage unless he says use a mesh current, then use a mesh current. And then that's what my rule of thumb is. You can use any method you want, but that's what I find simplest. Okay. And so this first one here, the arrow going to the left is going to be V1. And then if we look, oh, shoot, it hits a current source. There's not another node with a voltage. So remember when we're forming these, it's going to be voltage over resistance to give us current. And so we look in this 4 amps in the opposite direction. So it's going to give us a -4 amp here. And that independent source is driving, like Fady said before, so we don't need to take into account this 28 ohm resistor. Okay, so we know -4 amps is that arrow going to the left. Let's look at the arrow going down. It's going to be V1, and then look, this 5 volt source, it's going in the opposite direction. So it's going to be V1 minus 5 volts all over 7. So plus V1 minus 5 all over 7. And then this arrow going to the right is going to be V1, where it starts, minus V2, the other essential node, all over 14. So V1 minus V2 all over 14. And then set that equal to 0. Then this second voltage is we're going to have to make an equation for. So V2, it's going to be, let's make our arrows. So one going to the left, one going down, and one going to the right, what's coming out. So V2 minus V1 all over 14. All over 14. And the next one is going to be V2 all over 10. And then the third one is going to be going to the right here, V2 minus V3 all over.
Oh, hey, Brian.
Yeah.
Forgot about the 28 ohms, right?
You forget about the 28 ohm resistor here because we have an independent current source. And so that independent current source, we do not need to take into account this 28 ohm resistor.
All right.
Because it's an independent source. And so when you write your equation going through this terminal, it's just going to be that 4 amps is going to be through it. Because remember, this resistor is in series with this current source. So the current going in must be equal to current coming out, because in a series combination right here, we have a series combination, that current going through is the same. So the 28 ohm resistor does not affect it. Okay, so right here we have plus V2 minus V3 all over 20. And then set that equal to 0. And then this last one here, it's going to be V3 minus V2 over 20. And then, oh, we actually noticed here, this is a good point for everyone to see. See how this, I'm going to go to the diagram on the left. At this node, it's at the potential -6 volts here. And so that's a pretty big part here because, oh, sorry, it's actually at 6 volts, sorry, not -6, because remember the current goes out of these. And so that'd be in the same direction going through the source. So it's at,
I think it's -6.
you think it's -6?
Yeah, I think it's also -6, just like the problem number 1.
Did I? Let me see. -6. Oh, okay. You guys are correct on that. I keep making that same error. Okay, so with these, it's -6 volts because the reason being is because the negative terminal is at that side. It's not the positive terminal. So it's at -6 volts. So what you're going to do here is for your V3, it's going to equal -6 volts. And so, oh, sorry, that came out wrong. Okay, So now that we know all that, what we're going to be able to do is we can plug that in. And so when we're going to plug that into the equation here, that's going to cause there to only be two unknowns, and then we have two of these equations. So let me draw it out in a different color. So this V3 here, it's going to apply to this one here. So that's going to become a positive 6. I'm just going to take out this. So plus 6 here is negative times negative 6 would give a positive 6 value. And then we're going to simplify these equations. And so if we simplify this top one here, what we're going to get is 1/7 plus
My bad, Brian. Before you continue, let's say there was a resistance right above the -6 volts. Then we'll have to write like a whole equation, right?
Yes. So for this V3, you would have to write a whole equation like we had in V1, because see how we have a resistor here?
Yeah, so what about the 8 ohms to the right? Do we just completely ignore that too? Because we know the voltage is -6?
What we do is, because we know at V3, it's at this potential of -6 volts. And so since we know it's at this potential of -6 volts, it's not going to be affected by any of the others resistors. It's sort of similar to this argument here of this current source and how this 28 ohm does not affect it, because this current source is the series. It's a series combination right here. So the current going through the 28 ohm is equal to the current coming out of the 28 ohm, because they're in series. However, here we have a voltage in parallel with this 8 ohm. And if you remember, the voltage drop is the same across parallel elements. So that 8 ohm is not going to affect the voltage. Does that make sense?
Thank you. Yeah, that made perfect sense.
Okay. So now what we're going to do is we're going to simplify these equations. And so we're going to get our V1 and V2. And so let's combine terms here. And so I'm going to get 1/7 plus 1/14 for my V1. So when I do that, I will get, nasty number. So I get 3/14 as the fraction. Let's do that instead. So I'm just going to simplify here to the left. So 3/14 V1. And then for next one here, we're going to get V2, so -1/14 V2. And then for our constant value, I'm going to move that over to the right side. So we have -4 minus 5/7. So -4 minus 5 divided by 7. And then move that over to the other side. And you will get -33/7, positive 33/7. So not a super nice number. And then down here for the second one, you're going to get -1 divided by 14. And that will just stay the way it is. So -1 divided by 14 V1. And then for this V2 here, you're going to get 1/14 plus 1/10. And then plus 1/20. And what you'll get is 31 over 140 V2, or sorry, yeah, over 140 V2. And then that's going to be equal to, and what we get on the right-hand side is -6 divided by 20, and that will be -0.3. And so now that we know this, we can plug this into our calculator. And so when I go here to the solving systems, we'll get 3 divided by 14. And then here you'll get -1 divided by 14. And then we can delete this third term here. And then it's equal to 33 divided by 7. Then here we get -1 divided by 14, 31 divided by 140. And then it's equal to -0.3. And then solve using the inverse. Let's see. We have 1, 2, and then we have two equations. Oh, oops, sorry. There we go. And so this is what I get. Let me see, what did he get? When I solved this on mine, I got 2004 divided by 83. 24.14, that is correct. So that's what you should get for this one. And then for the next one, 534 divided by 83. 6.43, which is correct for V2. And so your value for V1 should be, let me just do this in text here. V1 should equal 24.14 volt. V2 should equal 6.43 volt. And then V3 should be -6 volt, like we determined up there. And so now that we know that, we were able to solve this one right here, number 5, the voltages at all the essential nodes. And so what we did is we combined, and then we noticed there was not any need to do a super node because there was no voltage source between any two nodes here. And so we went by each one. We noticed there's a current source here. So that current source would just be the one we needed going through up here. We noticed also this voltage source determined the potential at this node. And so we're able just to write for V3 -6 volts. We solved it using our node voltage methods and got these 3 solutions. Okay, now that we recap number 5, let's do number 6. Label the mesh currents and write the equations for the mesh currents and solve. Okay, so now when we're doing mesh currents here, what we need to do is I'm going to create one loop here, and create one loop here, and one loop here. Remember when I told you guys form a super mesh, and that occurs when there's a current source between two meshes? Look right here, there's a current source between I1 and I2 here. So we're going to have to form a super mesh of the combination of I1 and I2 here. We'll also have our loop I3. And so I'll just draw that over here. Our super mesh is going to look like this. So it's going to start here and go here. And then we're going to make a third equation for that current source. And so let's start with the big one, I2 plus I1 plus I2. So I1 plus I2, what that equation is going to look like if we're going through is, let's start at the 4 ohm resistor. So 4 ohms times I1 plus, and then 6 ohms times I2. And then look at the current. And so since we made a mistake last time and now learn from our mistakes, so it's going through the positive terminal, the current. So it's going to be a positive number here. So what we're going to do is we're going to add, and then it's going to be 4 volts here, and plus this 9 ohm resistor, the current from I2 is going through it, but in the opposite direction, we have I3. And then we have this 7 ohm, and that's going to be I1. And then in the opposite direction, we have I3. And then we add this 2 ohm resistor here. That's going to be I1 going through it. And then we're going to have this 10 volt source. And that 10 volt source is going to have the current going in the opposite direction. It's up the negative terminal. And so that's going to produce a negative voltage. And so we're going to say negative 10 volts here, set that all equal to 0. And so now that we made that huge equation here, we're going to have to make an equation for I3 down here. So I3 is going to be, and let's look at it here. It's going to be 7 ohms times I3 minus I1 plus, and then 9 ohms here. Then that's going to be I3 minus I2, and then plus, and we're going to have 12 ohms times I3. Then set that equal to 0. Okay, now that we know the equations for I1, I2, I3, remember, we're going to have to make an equation for this source right here since we made a super mesh. So we have I1 going through it and I2 going in the opposite direction. And so what we need to do right now for that 4 amp source, I'm just going to say 4 amp source, equation here is it's going to be I1 minus I2 is going to equal the 4 amps because I1 is going in the same direction as the 4 amp current source. Okay, now we got our 3 equations here. Let's combine terms. So let's simplify this. When we simplify, let's start with the big one. So I'm going to do simplification here, I1 plus I2. And so combine like terms, what we're going to get in the end is it's going to be 4 plus 9, wait, no, 4 plus 7, 11, plus 2, that's going to be 13 ohms times I1. Okay, let's look at I2, 6 plus 9, 15. And so plus 15, I2. And let's look at I3. It's going to be -9 minus 7, so -16 ohm times I3. And then go to the right-hand side, all the constants. So 4 plus 4 minus 10, -6, go to the right-hand side. That's going to be 6 volts. Okay. And so now that we made the equation for that one, we're going to have to make an equation for the next one here, which is going to be, let me draw it out, I3. And for I3 here, it's going to be this -7 for this one. So -7, and then I1, and then plus this. For I2 terms, it's going to be -9. So negative times I2. And then I3, it's going to be 7 plus 9, 16 plus 12, 28. And that's going to be equal to, and then looking here, it's going to be 0. Okay, now that we made our I3 equation, we're going to have to make the we're looking at this 4 amp equation, I1 minus I2 equals 4 amps. That's just going to be our third equation down here. So we don't need to simplify that any further. So I1 and then minus I2 is equal to 4. And so now that we got 3 equations and we have 3 unknowns, I1, I2, I3, what we can do is we can plug this into linear systems equation solver. And so when I plug it in here, what we need to do is, let me clear all this. For the first equation, I have 13. For the second one, I have 15. And then here I got -16, and then I got 6. And then here I got -7, -9, and then 28, and 0. And here I got 1, -1, and then 4. Okay, solve using the inverse matrix. Let's look at this. And what I'm going to get as a result, 53 over 22 gives me 2.41. So I got 2.41 for I1. So 2.41. And then here for the next one, -35 divided by 22. I got -1.59. And then for the third one here, 1 divided by 11, I got 0.09. Okay, so that's I1, I2, and I3 here. And that is what you should get. And I checked that on simulator, so that is the correct result, comparing it against mine. And then he doesn't solve it exactly in his, but those are the numbers you should get. Okay, now for our next one, go into number 7, source transformation. We can use source transformation here because we have no dependent sources. Big key idea to take away. Okay, so for number 7, let's look at this. Start from the leftmost and go to the right. Okay, I see a voltage source. There's a resistor in parallel with the voltage source. That doesn't happen. So we can just ignore this resistor here. Same thing, if you have a current source and it's in series with a resistor, get rid of that resistor. Don't take it into account. So right here, we have this voltage source in series with this 10 ohm. So what we're going to do is we're going to create, I'm looking at this right now because what's going to happen is this 10 and this 4 down here, if you see it, remember how I told you guys for voltage sources, if there's a resistor in parallel, ignore it. There's a current source here. This resistor is in series, ignore it. Just make sure to do that because you might forget later down the line. So now what we're going to do is we're going to make a Norton equivalent right here. So 5 volts divided by 10. When I do 5 divided by 10, I get 0.5 for my amp. So 0.5 amps here for current. And then right here, it's going to go up. And we're going to have now this 10 ohm in parallel. And then we have this current source on the other side, which is 1 amp. And so remember how I told you guys, you combine current sources in parallel. So this 1 amp plus the 0.5 is going to be 1.5. And so what I'm going to get as a result here, I'm just going to draw it down here.
Wait, Brian, isn't it, since the 0.5 is going up and once it hits the 1 amp, it should be going down? It should be flowing down to the negative. So that means it's 0.5 minus 1, not plus 1.
It would be, if we look at this, what's going to...
I looked at the way the professor did it, like you're correct. That's the same way the professor did it. I'm just asking for my own sake because I thought if it's going up, and I mean, our current is supposed to usually, I mean, if we're doing node voltage, we usually say that at this node, current is supposed to be going to the right, to the left, and down.
You remember how I said you add current sources in parallel?
Yes.
They have the same reference direction, so we add them together. What I like to think is this one's going up and this one's going up, add them together, they're going in the same direction. Like 2 rockets going up is going to equal 1 rocket going up as well. If they're in the opposite direction, you subtract them because this rocket's going up, this one's going down. Where's your position? If you want to track both at the same time, it's going to be in the middle there. So you're going to have to subtract. So if they're in the same reference direction, you add them. That's the same if you have voltage sources in series. They have to be the same polarity. So here and here. And so you add them if they're in the same direction. Same polarity. But if they're in opposite polarity, you subtract them. And the reason being is if I have like 3 amps here and I have 2 amps here, we have to add them together to make 5 amps. And so if they're in the same direction, however, if one goes down, you have to subtract. It's sort of just, I think, accepted, and I know what you mean. They're going and they're gonna, this one's gonna hit this one.
I usually think of a circuit as a loop, you know, if it's something.
It's one thing you have to accept for source transformations, because source transformations is a different method than node voltage or mesh currents. So that's the way it's accepted in source transformation, because you can choose 1 of 3 options. Here we chose source transformation, and that's a rule that you have to add them in parallel, these current sources, and they have to be in the same reference direction to add. If they're in opposite reference directions, you have to subtract.
Dope. Got it. Thank you so much, bro.
So that's why it's a different method, Fady. Source transformation is different from node voltage and mesh current. Okay. Now that we cleared up any confusion, ask questions, guys. It's good to know. It helps me think as well, so it helps me too on the exam. And so it'd be boring if no one was asking questions. So what we have here is...
my bad.
Yeah.
I kind of missed out the part where you got 0.5 ohms. Is that because you
0.5 amps here?
Yeah.
What I did is I took 5 volts and divided it by 10. Got 0.5 amps.
Got you. And the 10 resistor
it becomes in parallel because we just now made a Norton equivalent from this combination.
Cool, thank you.
And then we combine the 0.5 amps with this 1 amp source now, because you can combine them in parallel for source transformation. Then we have the 10 ohm here. And then we have a 2 amp going down. And so 2 amps going down, if we combine them in parallel, this 1.5 going up, 2 amp going down, that's going to result in a 0.5 going down. And so now we know that. And then we have this resistor in parallel, which is this 10 ohm. And Then we also have beyond this another 10 ohm. Remember how if two resistors have the same value and they're in parallel, it's going to become an equivalent resistor that is half. And so this would be 5 ohms. And so then here we're going to have 0.5 amps, and then we're going to have 5 ohms. And then because 10 times 10 divided by 10 times 10, that would be 20 divided by 100. Wait, 10 times 20. Wait, 10 times 10 divided by 10. 10 plus 10. Or sorry, 10 times 10, 100 divided by 20, and then that give you 5. So it's half. And so then we have this 8 ohm resistor up here. So have this 8. So what we need to do is we need to create a Thevenin equivalent. So this 5 ohm becomes in series with the voltage source in order to produce our final here and get our Thevenin. And then we'll convert that finally to a Norton equivalent because it asked for it. So 5 amps times 5 ohms, that gives us 25 for a voltage source. So down here, because the current source is going down, that's why we have the positive on the bottom. So we have 0.5 times 5, that gives us 2.5 volts. And then we have that 5 ohm resistor is now in series. And then we have that 8 ohm in series. So that's just going to combine to be 13 ohms. And now I'm going to create the Norton equivalent because it asked for that. So 2.5 divided by 13 gives me 0.192, which is 192 milliamps. And then that current's going to be going down, same direction as that voltage source. And then here that 13 ohm is going to be now in parallel. And then we have terminals A and B. And that was our Norton equivalent. So now we solved another one using source transformation. And number 8, solve problem 1 using superposition to find the voltage on the 2.5 ohm resistor. Which method is easier? So using superposition for number 8, sorry, for problem number 1, to find the voltage on the 2.5 ohm resistor. You guys already know how to do source transformation, so I'm going to go more examples. But for this one, we noticed that node voltage method was easier. And the reason being, since we do not have to evaluate each of the independent sources, which is time consuming. So that was the annoying part when you had to do superposition here. But now that we know that, number 9, which value of load resistor connected terminals A and B of problem 7 will give maximum power transferred to the load? What is the efficiency of the circuit expressed as a percentage of total power going to the load? Okay, so we know max power. Honestly, I just memorized the thing. Max power, do not memorize this derivation. If you ask for it, you can just have it on the side. The max power occurs when the R Thevenin is equal to the load resistor. And that's when that's given. I do not like derivations too much. So I just like memorizing the stuff I need to know, not 20 steps. And so what's the efficiency expressed as a percentage of total power going to the load? And so what we need to do is to find the efficiency. The efficiency is going to be the resistance of that load resistor divided by the total, the power through the load divided by the P total, and then so the entire power within that circuit, and then times that by 100%. And that'd be the efficiency. And so how much is going through that load versus the total times that by 100. And so what we need to do is we're going to connect, we found our V Thevenin circuit for number 7 just through the past calculation. And when we did that, we had 2.5 volts. So I'm going to draw it over here. So we had 2.5 volts down here. And then we had that hooked up to a 13 ohm resistor. And then we had our terminals A and B here. And what we're going to do now is we know the max power RThev has to equal to R load. So remember, this is our VThev and our RThev right here. So the value for VThev we got was 2.5 volts. So knowing that, we can just say the R load has to equal 13 ohms because the RThev is equal to the R load. And then the power of the load, for the efficiency, what you can do over the power generated times 100%, I calculated the power going then through that load resistor. And if you guys remembered from our Norton equivalent circuit, we could tell the current as well going through here. But one nice thing to know about power, remember you can rewrite the power equation different ways. So P load could equal I load times V load voltage times current. It could also equal V load squared divided by, and then that would be R load. And it can also equal, if we have here I load and then I load, then that'd be I squared R. And so then I load squared times R load. And so V squared divided by R, and then also I squared R. So you can write the power equation 3 different ways to find the P load. And so what we know here from our Thevenin and equivalent is we know the resistance of the load. And if we wanted to determine the voltage drop across the load, what we could also, or the current going through the load resistor, we can find that using just, if you guys recall from the class 1, if we have a resistor right here, so that's hooked to terminals A, B, and we want to find the current or the voltage drop across it. Remember, if we had the voltage from the source, this is going to be using voltage division here. So remember, for voltage division, it's going to be the voltage of what we're interested in. So I'm going to say V of the 13 ohm, if we want to find the voltage drop across it, is equal to the voltage by the source, which would equal 2.5 volts. And then if you guys recall, it's going to be the resistor you're interested in, which is the 13 ohm, that R load, divided by the resistor you're interested in plus the rest of the resistance in the circuit, which is 13. And so then when we solve this equation, 13 divided by 26, that's 1/2, so 2.5 divided by 2. When I do that, I'm going to get 1.25 volts across this R load. And that makes sense because half the voltage should occur across here, and then half the voltage should occur across here. And so I'm going to have 1.25 volts across this one and 1.25 across this one here. And we can plug that now in to find the power across that load resistor here, this 13 ohm one. And so knowing V load, which we have is 1.25 volts squared.
Did you like introduce that 13 ohm resistor as like a load like resistor?
Yeah, because remember here, Rthev is equal to R load, and our R Thevenin was 13 ohms. And so that's why I said our R load was 13 ohms here. So I just attached that to A and B.
Okay, and then you just did regular voltage division.
And I found how much voltage is going across that load resistor now here. And so it's 1.25 volts divided by the resistance of the load, which is 13 ohms. So 1.25 squared divided by 13. I got 0.12 for the power. So I'm going to write, I'll just write it in milliwatts because that's easier for the power of the load. And so the power of the load in milliwatts is equal to 120 milliwatts. And now let's find the power generated. And so the power generated, I'm going to just say that's the P total because the power generated is the total power that is going to be used through the circuit. And so P generated is going to be what's the power by the source. if we think about this, we know the voltage is 2.5. And what we need also is, do we know the amount of current that is going to be going through? We could also notice the amount of current that would be going through would be, think of the Norton equivalent. That told us the current for it, but we know the voltage. But okay, here, let me just solve for the current to make it easier. So the current going for the circuit, if we think about it, the voltage from the source is going to be equal to the current times the resistance within the circuit. And so we're going to have 26 ohms because it's going to be the R load plus the R thev in this completed circuit. And then the current we don't know, but the voltage from the source we know is 2.5 volts. And so if we solve for I, the current going through the circuit would be 2.5 divided by 26 ohms. What I get is, for our specific current, let me write it down here. I is equal to 96.15, and then that'd be milliamps. And so since we know the value for the current, what we can do is we can find the power generated for the entire circuit. So the power generated, which is P total, that's going to be equal to the current from the source, which is 96.15 milliamps, and then times the voltage for that source, which is 2.5 volts. And then when we, because power is equal to I times V, when we do 96.15 milliamps times 2.5, what I get is I get 240 milliwatts. Okay, now that we know that, we're going to have 100, this equation right here, we can plug into now. So the power for the load resistor is 120 milliwatts. And then the power from generated within the circuit is going to be 240 milliwatts. Multiply that by 100 to get the percent to get the efficiency, and that will be 50%, because that's 1/2 120 divided by 240 times 100, 50%. And that makes sense, is 50% of that power is going to be dissipated by the load resistor, and the other 50% is going to be dissipated by the Thevenin resistance resistor. And so that should add up to how much power is generated, because the power dissipated, it has to be equal to the power generated. And the power generated here is the power from the source. And so those resistors must be giving off the same amount of power that is being generated, because power energy is conserved. And so that's how we know it. Okay.
Oh, yeah,
Now
Brian. Oh,
what?
my bad. So for where'd you get it? It's the 240 milliwatts. Was that I mean the 96.15 milliamps. That was, did you do current division right there, or?
If we I solved right here, sorry, I know it got a little messy, but how I solved for the current is I had the voltage of the source is equal the current going through the circuit times the resistance of the circuit. We had 26 ohms here because we had the 13 ohm resistor for the Thevenin resistance and the 13 ohm from the load resistor. Add those two together, they're in series, 26 ohms.
Oh,
and we don't know the current, but we know the voltage. Yeah, and then we know the voltage by the source. Yeah. That's how we found I. Power is equal to current times voltage. And so I got the current times voltage and found the amount of power. So that was the power generated, and this was the power by the load resistor. Multiplied that by 100, you get the percent efficiency.
Cool, thank you so much.
Okay, now that we answered all that, that is the main of chapter 4, which was the most important chapter according to him. And so if you guys can get down that, you'll be pretty good. Okay.
Well, I don't believe him. I know he's gonna fuck us with op amps.
Okay, yeah, okay, I'll do op amps examples. He didn't give us any questions at all on chapter 6 in his worksheet. So I'm thinking you guys are probably chilling on chapter 6. I'm not going to study up much for it, but let's do some op amps practice here. When I first saw this, it was a little weird. So don't worry, you're not alone. I was like, what the heck is happening? So do you guys want to do this one or the hand? Probably that. I'm thinking it's going to be more the handout, to be honest with you guys. So let me just do those.
Yeah, let's do like two of the big ass problems if we don't really have time for a lot of chapter 6.
Yeah, okay, let's just do the handout ones. Okay,
Bet.
number 1. Design an inverting amplifier to provide a gain of 25 using practical components. Okay, we have an inverting amplifier. So here, it's gonna, our amplifier, I'm gonna have a positive and negative terminal, and then it's an inverting amp. It has negative feedback, if we remember, because inverting amp is a closed loop. And so here we have our feedback resistor, and then we have our other resistor, which you just call RS. And then you have that the source is actually provided to the negative terminal. So that's how it's inverted, where there's just a ground connected to a positive terminal. If it was non-inverting, the source would be connected to the positive terminal. So this is our RS here. And here's our output voltage. And so if we remember our equation for the inverting amp, you just got, you can either derive these or you'll literally just start memorizing them after a while. RF over RS times V in. And so what I did is here, we know this right here is our V in, so you guys know. And so what I'm going to do is if we want a gain of 25, that means RF over RS must be 25. And he had a resistor ratio, literally just stay in the kilo ohms. That's what you should do. And I think it was like above 100 or something, or above 1,000. I think 1,000 to 1 mega ohm. So just use kilo ohms. If he says design anything with resistors, use them in the kilo ohm range. So if you want to,
Ryan, the gain is always the RF over RS, right?
yeah.
Oh.
So right here, what I'm talking about, this part is the gain here. And then the other one is your voltage that's going to actually be amplified. So the input voltage that's amplified here. And so the RF over RS, if we want to gain a 25, set RF equal to 25K, set RS to 1K, 25 divided by 1 gives you 25 for your gain. So what I'm going to do here is I'm going to make this resistor 25K, and then the next resistor is going to be 1K. Okay.
Oh,
now
I had a question for this one because you know how the equation is just for the gain, the equation is negative RF over RS. Yes. Why don't we do, or like what happened to the negative there? Or do we not?
Okay, the negative, do you guys remember is going to be going back to this one here, the regular compare. Oh, I think they have actually diagrammed that. Let me not spend my time drawing that. Over here, see this comparator here, where the gain is the reference voltage minus the input voltage, and the reference voltage is hooked up to the positive terminal, and the input voltage is hooked up to the negative terminal here. Since we have the voltage hooked up to only the negative terminal here, we don't have this reference voltage. So it's the gain multiplied by the voltage coming in for the negative terminal, and we have the negative in front of it. That makes sense, because it's always gain times VP, what comes into this. So VP, remember here, minus VN, because it does the voltage difference between the positive and negative terminals. And so since we have 0 volts, we have it connected to ground here. It's going to be negative VI times the gain.
Gotcha, okay.
Okay, hopefully that clarified. Okay, and now that we've done that, let's continue. So we did a gain of 25. If this amplifier is connected to a signal generator that produces a 20 millivolt peak-to-peak sine wave at 1 kilohertz, what is the ideal output voltage? Okay, so right here we have 20 millivolts peak-to-peak, and then it's sine, and it is 1 kilohertz. Okay, and so now that we know all that is for our voltage source here, what we're going to do is I draw it out in order to understand it. So what's coming for input, we have a 20 millivolt peak to peak. So that means we have 10 millivolts going up, 10 going down, 10 up, 10 down. So I'm just going to say this is 10, and then this is in millivolts, the scale here. And then this is -10. And then we have this with time. 1 kilohertz, remember the period is 1 over the frequency, so 1 divided by 1000. And that gives us 1 millisecond. So at this point, it's 1 millisecond. At this point here, it's 2 milliseconds. So this time is going to be milliseconds here because period is 1 over the frequency, so 1 over 1 kilohertz. Okay, I know the input voltage, and what is the ideal output voltage? Plug it into your equation here. Remember, gain was 25, and then the input voltage was 20 millivolts peak to peak.
Yo, Brian, what if it wasn't peak to peak? Would that make any difference? Like if it was
Yes,
just 20
because
millivolts?
then if it was like, let's say just 20 millivolts peak, that would mean you're going up 20 and you're going down 20. So it'd actually be 40 millivolts peak to peak. So in your answer for my output voltage right here, I have to clarify that it's peak to peak. So it would be 20 millivolts. So 20 millivolts times -25. That gives me -500 millivolts peak to peak. And that's what I get as my output voltage here. And so if it were to just say 20 millivolts peak, you will have to clarify in your answer that it would be 500 millivolts peak. It's not peak to peak, because that would also tell you your sine wave, how much it goes up and down. And
So the output is unit pretty much, whether it's peak or peak to peak, just match. But when it comes to plugging in the numbers, it doesn't make any difference.
no.
Okay. Gotcha.
You couldn't multiply by 2 to get the peak to peak if you were only given peak and then say your outputs in peak to peak, but literally just stay the same or you'll make mistakes. Now that we did that, since it's peak to peak, remember this is really -250 in one direction and then +250 in one direction, -250 and +250. So down here it's -250 and up here it is +250. So now that we found this output, we are good. So we know this output voltage is -500 millivolts peak to peak. So it goes down -250 and up 250. This is an inverting amp. Look, it's opposite of the input. It goes up in the input, it goes down for the output. It also amplifies. Look at the gain of 25. It goes from -10 to -250. It goes from 10 to +250 for its peaks. Okay. Number C, most signal generators have a 50 ohm source resistance. How will this affect the output voltage in your design? Okay, so if we have a 50 ohm source resistance, think right here. There's going to be a source resistor right here, and that's going to be 50 ohms. That's in series with our RS. So it's not going to become 25 or gain. Our gain is going to be reduced since it's a bigger number for RS. It's now 1K plus 50 ohms. And so that's going to cause there to be a smaller gain because you're dividing by a larger number. So what's here is smaller gain for part C. And then what is the maximum frequency that your amplifier can faithfully reproduce? Max frequency, it can faithfully reproduce. This one is a good one because it stumps you. And I had the same exact question when I asked. I had to go to the tutoring center in order to understand this one because he didn't cover it in class. And what I got for this one, let me find it, find out. I know Brian doesn't know everything. Sorry, guys. Let me see. I know how to do number E. So the max input voltage that you can faithfully reproduce. But let me find out how to do. No, this was handout 2, so I think it's in the beginning. up in Dropbox. Okay, here we go. Okay, so how you do number D is you have to think about the gain bandwidth. And so the max frequency, it can reproduce as the gain bandwidth ratio. And if you guys remember that, it's typically 700 kilohertz. And that's for the 741 op amp. Okay, and so for part D, we know the gain is going to be, okay, sorry, I'm just going to put this right here for number 4. We know the gain is 25. That's what we want. So 700 kilohertz divided by 25, our bandwidth is going to equal 30 kilohertz. That's the max frequency your amplifier can faithfully reproduce. Okay, now that we talked about the gain bandwidth equation, the maximum input voltage your amplifier can faithfully reproduce, that is going to be, remember how amplifiers have a positive 15 and negative 15 normally, he said, as the supply voltages, so positive 15 and negative 15. When he said that, you recall that the output voltage can approach at most within 1 volt of those values. And so what we're going to have for output voltage, remember how we said it's equal to negative RF over RS times Vin. So what we can do here is we know the RF over RS, we can just say that our gain times the input voltage, so we can rewrite this as gain is equal to the output over the input voltage, and our gain is 25, we know in this equation, and the max output is going to either be positive or negative 14 volts, because it can go within that for our op amps. It can approach the supplied voltage by 1 volt, which the supplied voltage is usually plus or minus 15 volts. So it can be plus or minus 14 volts over the input voltage. And this input voltage is going to be 14 divided by 25 when you do it, and that would be plus or minus 0.56 volts. And so that's the, what?
Oh, just finish that problem real quick. I'll ask after.
Okay. So that's what I learned on it. The max input voltage that your amplifier can faithfully reproduce. What do you say, Kato?
All right, so for the 750 kilohertz, I wrote down on my paper that just a typical value for gain. Is that only for inverting amplifiers or like any amplifier?
Okay, when you look at the, okay, because you remember how in his lab class, he talked about this also in his regular lecture section, everyone. It was the the micro amplifier 741 IC chip, and it basically is an amp within it. And so this chip, it has a specific gain bandwidth ratio, and for his, he had it at 750 kilohertz. And the reason being is he did a calculation here where he found it in decibels, and then it lined up to the 750 kilohertz for this specific chip. And so that's where I get my normal 750 kilohertz. He did, I forgot the exactly how he calculated it, but I think it was in his laboratory where he did tell us the normal value for this IC chip is 750 kilohertz. So he had a specific calculation behind that where he was able to get the decibels, and that's how it's accepted. So that's what I use for this. For the gain bandwidth, you guys just know for that chip, it's 750 kilohertz.
Am I tripping, or did you say like these questions weren't like D and E aren't going to be on the test, or did I just like completely make that up in my head?
Does anyone know?
I really hope so, because these kind of questions like D and E, like that's so fucking anal. Like, what the fuck?
Yeah, I mean, I'm hoping he doesn't put that on the test, but if it does, at least we know now. So thank you, Brian.
Okay. Now part 2. For question number 2, design a non-inverting amplifier for a gain of 100. And so non-inverting amplifiers, they have the voltage hooked up to the positive terminal, so it's not inverted, this input voltage. And so here we have our inverting amp here, so positive and we have negative. And we have this to 0. And we're going to have a feedback resistor here, so RF. Then we're going to have RS, the other resistor, and that should be right here. And then we have VI here, and we have our output voltage here. So our equation for V out, it's going to equal 1 plus RF over RS, and then that's the gain times the input voltage. So the gain times the input voltage. And remember, this one is positive because if you look back at that comparator, remember it's at the positive, so it's VP here. There's no voltage for the negative terminal, it's set at 0 volts. That's why that negative sign cancels out. So we only have the positive times the gain. So here it's only a positive value.
Brian, quick question while you're at it. Can you scroll up real quick again? Do you see in the voltage comparator, the very first one, it says V naught equal G, V reference minus VI.
Yeah.
But since we already agreed that G is the value of resistor RF divided by RI, but we don't have any resistors here. So what would the value of G be then?
The gain in an open loop is infinite. And the reason being that the gain is infinite is because this is a good question, actually. That is crazy, and it took me a little while to understand. Okay, what happens is if you guys see here, remember how the feedback resistor I always told you guys goes to the negative terminal here, and then we have RS? Well, what happens if we want it to be an open loop? Remember how no current flows through a short circuit? In a short circuit, you can think as infinite resistance since no current goes through. This value of RF is so great in comparison to RS because it's just an open loop here. There's no resistor actually here, that this gain is infinite in an open loop. However, in a closed loop, that gain is not infinite because you have it hooked back to one of the negative terminals. And so what that causes, because you actually have it hooked up with a resistor value, it causes the gain not to be infinite. It causes it to be a finite number. So up here, you can think of it as an open circuit. In an open circuit, no current flows through. So the value of resistance is infinite here for RF. And so that causes the gain to be infinite. However, for a closed loop, it's finite because you actually have the value for RF.
So for the first two, if we ever get asked about V output, it's always the value is going to be infinity.
For the gain,
not for the gain, for V naught, because or for V output, because I mean V output is the gain times whatever else, but since the gain is infinity, then V output should be infinity, no?
Okay, but remember that it's not going to be infinity because remember how I told you the rule that the voltage supplied, it can only approach by 1 volt. And so it would be plus or minus 14 volts, dependent upon what your values are for VR or reference and VI, because the gain can be infinite, but infinite, it has a limit for the voltage comparator that it can only approach 1 volt of the voltage supplied. And you'll have to know that. So the output voltage can only approach positive or negative 14 volts.
Okay, so for the second one, it's still an open loop, but yet we do have an RF and RS.
Yes.
So would the gain also be infinite, or would it equal RF divided by RS?
Here, the gain, see how they only give it for VP here? This one is not a closed loop because it's not hooked to the negative terminal in here. That's a different story. And so since it's not hooked up to there, the gain here, they would have to provide you. This is only used for solving the value of VP here. And because remember how we said VP is right here and VN is right here. And so what they use here is they use voltage division for V out. So I'm going to redraw the circuit. So V out looks something like this. And then you have RF, and then you have RS, and then you have it hooked here, and then that's hooked to ground. So they just wanted to show you that you can find RF, RS. You can find the value of VP because VP is going to be equal to, if you think it's at the same potential as RS, because look right here, VP, RS is just hooked to ground on the other side. So this would be at the same potential. So VP would be across this RS resistor here. So using voltage division, they got VP is equal voltage from the source, which is this output voltage, all over the resistor they're interested in, which is RS, over the resistor interested in, plus the other resistor, which is RF. Is that good?
Yeah.
Okay, so they would still have to provide you the gain fade. The only reason they had RF and RS in here connected to a positive terminal is that's an open loop, but that tells you how to find the value of VP. And then VN here is going to be determined by this VI here, whatever that input is. Okay, now that we talked about that, number 2, design a non-inverting amplifier for a gain of 100. Okay, so let me do this. Okay, non-inverting amp. The voltage source is hooked up to the positive terminal here. So positive here, and then the negative terminal is going to be hooked to ground. And remember, the feedback resistor is hooked to that negative terminal, and then we have the RS also. So RS here, RF here. The voltage inputted is to the positive terminal, and the output voltage. And so now that we have those, we have this with a gain of 100. So gain of 100, remember our equation, V out equals 1 plus RF over RS times V input, and RF over RS must equal 99, because 99 plus 1 is going to be 100 for a gain, because this is our gain right here, 1 plus RF over RS. Okay, so 1 plus our value here, I'm going to make 99K be our RF, and RS is going to equal 1K ohm. And now that we know that, what advantage has this design over the inverting configuration? The one benefit to the non-inverting amp is that the cool thing about it is the op amp's voltage is in phase with its input. The input resistance is infinity for this one, so it accounts for transducers. So you see non-inverting amps used more than inverting amps because the voltage source is hooked up to the positive terminal, but there's infinite resistance here. However, if the voltage source is hooked here to the negative terminal, it would be in series with RS and be causing that to mess up the gain here, and that would not be good because it would be multiplying the transducer's noise. So the reason we have it on the positive terminal is because there's infinite resistance here, and it won't affect the value of RS in this equation. And so that's why we use inverting amp. So here I'm going to say in phase with output because there's no negative sign, and also good for transducers. Since the input resistance does not affect RS of the transducer, does not affect RS, and therefore affect the gain. Okay, So now that we talked about that, for part B, if the input voltage is 0, what is the maximum range of output voltage using the chip operating at a temperature between 0 to 70 degrees? Okay, so input voltage here is going to equal 0 volts, 0 to 70 degrees Celsius. Let's go here, everyone, to the actual numbers. 0 to 70 degrees Celsius, that's going to be, let me see, on this page right here. And it said, what is the range of output? So when we're doing this, what they wanted to know for this specific portion was we have to take into account all errors here. And so the errors that we're going to encounter is offset voltage and input bias current. Because if you look down here, the errors that can occur when you're using any type of op amp is you do the normal equation. So your input voltage times the 1 plus RF over RS, the gain. So this is just the normal non-inverting amp. And then what happens here is then we have an offset voltage. And an offset voltage, what this does right here is you have to take that into account because some chips, they're not exactly, you can have some noise coming in and that can mess it up for your voltage signal. And then also down here is this one is input bias currents right here. So it in this final equation here, the DC error, it combines the offset voltage, the input bias current equation, and the regular non-inverting amp equation. Okay, so that's why you have a potentiometer here. So when you have 0 volts input, it accounts for this offset voltage and the input bias current because you're able to set the voltage output equal to 0. So they do not affect the value when you actually do have voltage coming into this regular non-inverting op amp. And so now that we talked about that, let's look at the conditions when the op amp is between 0 to 70 degrees Celsius. Okay, here, the input offset voltage for the full range. In full range, it means 0 to 70 degrees Celsius down here. And so when it's between that, it's 7.5 millivolts. So right here on the right, I'm going to add those equations for input offset voltage. So 1 plus RF over RS all over the offset voltage, times the offset voltage. And then the input bias current equation, that one is, I like to think of it as like V of P minus V of N times because if you do VP minus VN times the gain. And you can see right here in his, it's just the V of P minus V of N all over the gain. So what you do here is you look at the terminals and you're like, okay, this is VP here, and here's VN. And so when I'm doing this for adding, it's going to be R I of P times the RG, and that is the bias current coming into the positive terminal times the resistor from the source, because you have a source resistor here when you have input bias currents. So that's accounting for the source. So plus the minus IVN because it's VP minus VN. So this would be the input bias current coming in through the negative terminal. And that would be multiplied by the parallel combination of R of S and R of F, because IVN's this one here. And so it's in parallel technically if this is 0 right here. If we have 0 output voltage when we're testing this out, it's going to be 0 and 0 both hooked up here. And so those two would be in parallel, RS and RF, because they're both hooked to 0 and the other end they're hooked to each other. So there's two parallel components. And so that's where we get that right there. And then you need to multiply that all by the gain, which is 1 plus RF over RS. And then when you solve that, so what we have here, refresher, This is the regular non-inverting amp right here, this equation. This equation here is for the offset voltage. All you do is you replace the voltage input with the offset voltage. Here, it's the regular, you do the VP minus VN times that gain. Your VP is that input bias current coming in through that positive terminal times by that resistor, that source minus, so whenever he says a source resistor, that means you have input bias current. Minus the VN, which is the input bias current coming in for the negative terminal. And then since the output voltage should be 0 when examining this input bias current, that's why we can say RS is in parallel with RF, because RF is set at 0 volts as well. So they are both have 0 volts at one end and the other end are connected to each other. So they're in parallel. This equation then make sure VP minus VN over, times the gain. Okay. Now we understand where these three parts come from in DC errors. And so we're gonna plug in our values. And so we need to go back here. Remember how I said that input, let me erase this. We look at the full scale, so 0 to 70. The offset voltage was 7.5 millivolts here. So right here is 7.5 millivolts. And here for the input bias current, that was for the full range 0 to 70 degrees Celsius, it was 800 nanoamps. So here you plug in 800 nanoamps. And then here you would plug in 800 nanoamps for IN as well. And then we know our values for RF was 99K and the value for RS was 1K. Okay, going back to the problem. Okay, now that we did that gain, advantage input voltage, if the input voltage is 0, what is maximum range of output voltage using one of those chips at temperature between 0 to 70 degrees Celsius? Okay, now we're gonna solve for this actually. Let's see. Oh yeah, you're gonna skip it. Okay, but just learning it. So let me now write the entire equation out with the values plugged in. Output voltage is equal to the gain, which is 1 plus 99K divided by 1K ohm, and then times the input voltage, which we know was 0 volts, they said for part B, and then plus 1 plus this gain again, 99K ohms divided by 1K ohms, and then times the offset voltage, which is normally 7.5 millivolts. And then plus the input bias current. However, they never mentioned a source resistor in part B. So I'm just gonna, this would be 0 then for this side. But if you still have that, that would still affect the negative here. So IP, which is 800 nanoamps. They never gave us an actual one for the source resistor. So that would just be 0 minus, and then I of N, which is 800 nanoamps from that data sheet. And then the parallel is 99K ohms in parallel with 1K ohm. And then multiply that by the gain in finally. And so the gain would be 1 plus 99K ohms divided by 1K ohms. And then you'll get your output voltage. And when you do all that, after you lose your sanity and cry for like 10 hours, your output voltage is going to be between negative 670.8 millivolts and then less than or equal to the output voltage less than or equal to 829.2 millivolts. And that's how you solve 2B. Okay, now after 2B, 2C is if the input is a 2 kilohertz square wave of amplitude, 100 millivolts peak to peak, sketch the shape of the output voltage over time. Okay, this one's more reasonable at least. Yeah, no, honestly, no one would finish Cato. So don't worry, everyone, you're good. You're on the same boat. I don't think he'll ask that one, but it's good to know it because he might ask about offset voltage or input bias current. So it covers all three. So it is a good one for that reason.
Oh, Brian, so how I did B, I know you did like all of that, and I probably did it wrong since I got a different number, but like I just did plus or minus 7.5 millivolts times 100, and I got 750. I think I did that with the tutor.
Yeah, the only reason I say is because you have input bias currents also from that data manual. And so he says for all DC errors here, you have to take into account the offset voltage, the bias current, and the regular just non-inverting op amp here in this equation. And I'm taking into account every scenario because he will mark you off. If he'd be like, oh, what about like the offset voltage? Oh, what about the input bias current? Because that is listed in the manual. However, I don't think he'll make us reference the manual. He will provide us these values. If they give you guys a source resistor, that means there's an input bias current. So if he mentions that, let's look here. Let's see, is there? Yeah, look, part D. Has the source resistance of 10 kilo ohms. How will this be affected? Oh, that means we have input bias current because that's in the input bias current equation, that source resistor RG. And if we look up here at the non-inverting amp, when we have an input bias current, oh, let me look down here. I think he drew it actually with this one. See, the source resistor for input bias current is there. So when you have an input bias current, that means, and when you have a source resistor, that means you have a bias current going through it.
Gotcha. Okay. Thank you.
Okay. Okay, now that we talked about that, good example, everyone. Let's get to part C. And so now with part C, I'm just going to clear this up because I feel like it's a little crazy. Okay, if the input is a 2 kilohertz square wave of amplitude 100 millivolts peak to peak, sketch the shape of the output voltage over time. Okay, so here we go. Here's our op amp. It was a non-inverting, so we had our positive up here, negative, and then we had voltage source. And for voltage source here, positive, negative terminal with the ground. This one have RS, and then here RF. And then here, this one was hooked to ground. And then it said if the input is a 2 kilohertz, so here 2 kilohertz square wave. It said of amplitude 100 millivolts peak to peak. And it said sketch the shape of the output voltage over time. So this is our V out here. Remember here we set this feedback to 99K to, in this one to 1K to give us the gain of 100 for a non-inverting amp. Okay, so I like to always draw the input in order to see the output and verify that this is a non-inverting amp. Since it should only amplify and it should not flip the output wave. So 100 millivolts peak to peak. So we'd have it up, down, and up, and then down because it's a square wave, everyone. Then the period would be 1/2 kilohertz, 500 milliseconds. So here would be, sorry, not there, that'd be, here would be one period, which would be 500 microseconds, sorry. And then here would be 1,000 at the next one. This time is just in microseconds, so you guys know. And then the voltage here, this would be 50. And this would be -50.
Wait, this is part C, right?
Yeah.
So for the period, don't we do 1/2K hertz or?
Yeah, and when I did 1/2, K, I got 500 microseconds.
Oh, okay. Probably because I didn't type it in my calc. Cool, got you.
Okay, and then so I have 50 millivolts up here, and then I have -50 down here for the millivolts, and then, okay, let's look. It's a non-inverting amp, so it's definitely going to produce some type of gain. So what we're going to have here is, remember, output is going to be 1 plus the RF over RS, which we said our gain was then going to be 100 times that input voltage. And so our input voltage is going to be this 100 millivolt peak to peak. So what's going to happen is we're just going to amplify this by 100. So it's going to go up. Let me just draw over it. It's not to scale, but it's going to go up here by 100. Then it's going to go down by 100. It's going to go up by 100 and then down by 100. So this would then be 500 here. And this would be negative 500 millivolts. And that's what's going to happen for this amplifier. And that makes sense. It's a non-inverting amp, so it should not invert that wave here, the waveform at all. So hopefully that helps with that one. And then let's go to the next one. And for our next one, oh, BTW, the slew rate. I'm just going to cover that right here because he might ask you guys what slew rate is. So slew rate, what I think of it, it's legit the delay between switching voltage levels. And so for the slew rate, so you guys know, he either will provide it. If it's not provided and he says, what is it? Here, slew rate. It is 0.5. So it is 0.5 volts per microsecond. And so here it's going to be 0.5 volts per microsecond. So what we had here was we had our basic one of 1 times, so 100 times 100, 500, 50, and then that'd be 5. Okay. Yeah. Okay. So our slew rate, if we look at this, the voltage per microsecond, what we have right here is it's going to be 1,000 millivolts per. So let me do it here. 1,000 millivolts peak to peak for our output wave because it's 500 millivolts each way. And then it's going to be divided by that 0.5 volts per microsecond. And that gives you, if you just want to think of it, of how the units cancel, it's going to result in, so 1,000 millivolts, which is 1 volt divided by 0.5. That gives you 2 microsecond delay. So there's going to be a 2 microsecond delay here between. So I'm going to show it right here. Oh, diagram, different color. There's going to be a little delay right here. And when it reaches the end here by 2 microseconds. So it's going to take that long for it to fully switch over. So if I were to draw a line between the 2 points right here, this is going to take 2 microseconds to change from positive 500 to negative 500. Here, it's going to take 2 microseconds as well, and then 2 microseconds as well, and then 2 microseconds as well to go back up here. So that makes sense. Slew rate is just like the delay to change for this op amp. Okay, now that we covered that, what slew rate is as well, let's get to part D. If the input in C has a source resistance of 10 kilo ohms, how will the output be affected? Okay, so here, what we're going to have to take into account is everything we discussed. 100 millivolts peak to peak. Okay, so now what's going to be happening is up here in my diagram, I'm going to show you guys the addition. We're going to have a source resistor here, which is going to be RG. In RG, because said right in here, it has a source resistance. It's going to be 10 kilo ohms. Okay, how will the output be affected? So this output voltage, if you guys want to think about it, it's remembering his DC errors, how I told you guys the 3 equations you need to know for any possible errors when you're doing this is the output is going to be equal to just the normal. So this is an inverting amp. So 1 plus RF divided by RS times the gain. Sorry, not the gain, the input voltage plus. And then the next one is going to be offset voltage. So it's exactly the same written RF divided by RS. And then that's going to be times the V offset plus, and then the third one is the input bias currents, which I just remember VP minus VN times the gain. So IP RG minus IN, and then if it's 0 volts the output, which it should be when you're determining input bias currents, RS is going to be in parallel with RF. And then that's going to be multiplied by our value, which would be the the gain, because that would be the voltage. So VP minus VN times the gain, which in this instance, which would be 1 plus RF divided by RS. Okay, we know how those three equations now work. And so now that we know all that, we can plug in our values. So our output voltage is going to be 1 plus 99K divided by 1K. And then the input voltage here for this is going to be the 100 millivolts peak to peak, and then plus 1 plus the RF is 99K divided by 1K, and then the offset voltage for this op amp, he didn't include it in this part, so you won't need to talk about it because he didn't say in part D. Look at the data sheet and tell me what value it would be. So I'm just going to have in a 0 volts for this one. He did not specify for this part of the equation. Sorry, this part of the problem. And then the last one, he talked about the input resistance from the source. And so that's why I'm like, okay, we have an input bias current. So I did reference the manual, and we found that it was 800 nanoamps full scale range times that input resistance, which is 10K ohms, minus that 800 nanoamps, which comes again from that data sheet I showed you earlier, that value. And then the RS is 1K in parallel with 99K. And then that would be multiplied by the 1 plus 99K divided by 1K, the gain. And when you do that, you're going to get 10.7208 volts as your output voltage. And so
Brian, we used 1 plus RF divided by RS because it's non-inverting. So if it was inverting, we would
you'll
just
have to use negative RF over RS for each one of those.
Gotcha. Perfect.
So just fix this one here, fix this one here, and fix this one here. You'll be solid. Okay. Now that we talked about that one, you guys did good. Let's do number 3, which is design a 3 op amp instrumentation amplifier for a gain of 200. Okay, this one is that one with the common mode rejection ratio, which is a good topic to cover because that one is weird. Common mode rejection ratio refers to, like, if I'm talking to you guys and there's a radio playing in the background, how much is that radio going to get amplified out to you guys instead of my voice? So we want to reduce that noise. So that's where we use a 3 op amp instrumentation amplifier. I'm only going to memorize how that one works. I'm not memorizing the 2 op amp instrumentation amplifier because he's more on this one, because he says everything's built from this. Okay. So how this works is we have 3 op amps. So that's why 3 op amp instrumentation amplifier. Okay, going to his diagram. I like to see his diagram sometimes because make sure I do it right, but also to show you guys how it works. The 3 op amp instrumentation amplifier looks something like this. So he starts it out. You have, I think of like positive. On top, you always want to be positive. Also a sandwich, you can think like the positives on the outside, negatives on the inside. On bad days, you keep your negative emotions to yourself on the inside. When you're outgoing, you're on the outside, and so positive on the outside. Yeah. Okay, sad face. Probably no one enjoyed that. And then here, the 3rd op amp, just copy the 2nd one, just replicate. And then what we got here is we have RG here, and then we have a feedback resistor here. And then we have another feedback resistor here. And then in the positive terminal, this is where we're going to have, if we have a signal, we can divide that by 2 if we want. For what he wanted specifically, when I copied it over, he told us that for our equation here, what it's going to look like is it's basically going to have our VA here. So I'm going to call this VA. So for our first one, and then for our second one here, it would be VB. And so this one would be VB here. And that's hooked up to the positive terminal. And then this is the ground, so VB. So VA and VB. And then what's going to happen here is this resistor. We're going to have R1 and then R2. So, and then here we're going to have R3 and R4. And then this one's hooked to ground and the other is a feedback resistor because it goes from the negative terminal. All these go to the negative terminal, which are feedback resistors. So let me do text here so you guys can understand it. This right here is going to be RG. This one here is RF. RF. Here is R1. R2. R3 and R4. In order to make sure none of the common mode is sent to the output, R1, R2, R3, and R4 should be exactly the same. However, R1 should always be the same as R3 and R2 should always be the same as R4. Think of it as the ones across need to be the same. If you want to make everyone happy, make all of them equal. Okay, now that we've done that, what we need to do now is understand the process on the left and understand the process on the right. So what happens here is only the differential mode is amplified, but on this section, only the common mode, it's rejected here for our output. So what we should get as our output, it should be VB minus VA and then times RF over RG if everything works perfectly, but if it doesn't, then we're going to have to go through with another equation. And so this is what it should be ideally for the 3 op amp. So what should happen here is it only does the difference between the two, and then the third op amp here gets rid of any common mode rejection. That's what happens here. It just totally deletes all the common mode signal. But for our actual implementation here, I would follow his, let me pull it up here. For the handout, he had one posted here, so just get familiar with it. He put the 3-op instrumentation amplifier here, so you can see this equation. It's the voltage difference here. So that's what should happen is it should only be doing the voltage difference, none of the common mode. And then he did RF over RG here. And since he set R1 equal to R3 equal to R2 over R4, what happened is this would cancel because this would just be 1 here. RB over RA would be 1. And then here he had the 1 plus RF over RS. And reason being is, let me see, RF over RS. Oh shoot, he wrote that wrong in lecture. This should be 1 plus RF over RG. Let me see. Okay, so I think he did a little mistake in this one when he gave it to us because it is a non-inverting amp, so the gain should be 1 plus RF over, yeah, so maybe don't rely totally. I would just say here, instead of using that, I would just do 1 plus RF over RG divided by 2, because that's for sure going to be one of yours at least, or you can split it up so then you have RS and RS here. He just combined these to make an RG here. And And so then that's what he did. But you guys can just do instead, because he should have had a 1 plus because it's a non-inverting amp. You guys can tell it's hooked to the positive terminal. And so his note was wrong a little on there. But this is the equation you should be using. I suggest use this model here provided in his notes over the one he did in last lecture. And this one I just find simpler. But let's go back now to number 7. So let me clear this real quick. What you guys just need to take away as your main takeaways from this 3 op amp instrumentation is that we have the non-inverting amp because it helps to reduce, it has a high input impedance and it doesn't affect the RG value. So that's why we use a non-inverting amp. And then this amplifies the differential mode. And then here for the third one, this R1's equal to R3, R2 equal to R4. And so then that would get rid of any common mode signal because here what happens is we have a unity gain and it gets away of any other resistance in here. So it helps to reduce that common mode rejection ratio. And that's how the 3 op amp instrumentation amplifier works. So let me now just clear all of this and then go to the actual number 3. So I'm going to pull this up on the side and annotate this one for number 9. So for part 3, he said design an amplifier with a gain of 200. Well, we can tell right here, our gain in this equation is going to be these resistor values. So this is our gain here, and then multiplied by the voltage difference. So the gain to get 200, what you can do is for RF over RS, 1 plus, if we want 100 here, let's just do 99 for RF. So I'm just going to say 99K. And then for RS, it's going to be 1K. That's going to give us a value of 100 for a gain. And then the one over here, RB over RA, RB is going to be, then we need 2 for this one because 2 times 100 gives us a gain of 100. RB would be, let's just say 40K. And then RA would be 20K. And so 40K over 20K is 2. And so these ones across are equal, so you guys know. And so what we get here is our gain will be 200. So let me just do 200 here. And then multiplied by the voltage difference between the two, VB minus VA. And so to get our gain of 200, this is the resistor values. You could pick any that just give you 200. Just make sure to stay in the 1K to 1 mega ohm range. If the error in the resistance ratios is 1%, what will the CMRR become? CMRR, one equation you have to know, he went over this last lecture, is 1 plus the gain over the error in the resistor ratios. And so if we know this is 1% down here, we can say in decimal form, that's 0.01. And then 1 plus the gain, which is 200 in this instance. So 1 plus 200 is 201 divided by 0.01. I got, when I did that, if the error resistance, what will the CMRR become? Remember, CMRR is in decibels. So to convert this new decimal number, which I got as 20.1 kilo, sorry, to convert that to decibels, what we need is we do 20 the log of this value, and what we have for this value, that 20 log is taken from the 10 log of the V out squared over V in squared. The 2 comes to the front, and that multiplies by 10 to make 20. So it becomes 20 the log. And what this value is 20 log, and then plug that in. And I got as my value 86 decibels. Okay, now that I got that value, that's what my CMR became. If the common mode input signal is 60 hertz at 2 volts peak to peak, how much common mode signal will be present at the output? Okay, so if we have our common mode at the input, how much is going to be present at the output? Okay, going off this one, let me look. I think I low-key forgot that one a little bit from handout 2. I had to ask that in the tutoring center as well because he didn't cover that in class. Okay, let me find it. Handout number. Okay, here we go. So for this one, for part 3, see. Okay, this one is based off our equation for the common mode rejection ratio. So for part C, what we need to do, we need to go with our equation, which we know for common mode. Oh, sorry, you can see that. Common mode rejection ratio is equal to the amplification of the differential mode over the amplification of the common mode. So amplification of differential mode over this one. And when we solve that, what we need to do is we know the common mode rejection ratio. We just calculated that 86 dB here. And the amplification to differential mode here is going to be 200, it said in part A, over the amplification of the common mode. And so what we do is if we want to convert this to a decimal, remember because common mode rejection ratios in decibels, but if we want an actual decimal number, what we're going to do is we have to do the 20 log. So if you guys recall, it's going to have to be set equal to, we call this, oh, okay. Yes, that's it. Okay, sorry, I should have included 20 log here. I accidentally forgot that right in front of this. So this is 20 log right in front of this ADM over ACM. And so what you need to do is then remember the base. So here it's base 10. So 10 to the 86 decibels is going to be equal to, so we do base 10, 10 to the 86 is equal to, and then it's going to be our 200 over the ACM. And then this is going to be, let me see, I guess 10 to the 86. And then if we multiply, do 200, and then that 20, if we think about it, it could have gone up and been, that would be the 20 in front. So then if we divide the other side by 20, got 5 to the 84, let me see, is equal to 200 over ACM.
It's 0.5.
ACM, and then if we do ACM is equal to 200 divided by this number. I got
2 things. So I think it's 0.5, not 5, right?
0.5. Where?
And 10 divided by 20 is 0.5.
Oh, I did continue. Okay, wait, real quick. I just made this a little complicated. I feel like let me just make it simpler real quick to make it, because I know some of my notes, I did it a simpler way. So, okay, let me just draw this for text. Common mode rejection ratio is equal to the absolute value of A, 20 log of the absolute value of the amplification of the differential mode divided by the amplification of the common mode. And so because it wants more the amplification differential mode and less of the common mode. And so what we want to do here is we know our common mode rejection ratio was 86 decibels, and that's equal to 20, and then the log of that still. Let's divide both sides by 20 just to make it easier. So when we do the change of base, that doesn't affect it. So 86 divided by 20, when I did that, 86 divided by 20, I got 4.3. So 4.3 is equal to log, and then that's ADM divided by ACM, the common mode amplification. Then what you do is you do the base rule. So 10 to the 4.3 is equal to then what's in the square root, which is ADM divided by ACM. And then now you can plug in what you know. So 10 to the 4.3 is equal to that. And so what we're going to get is okay, so when you plug in, we know the amplification of the differential mode given by part A is 200. So 10 to the 4.3 is equal to 200 divided by the amplification of the common mode, multiply over your amplification of the common mode should equal 0.01. And now that we know that the output voltage of the common mode, if you think of normal equations, is going to be equal to the amplification of the common mode times the voltage input by the common mode. And so the voltage output by the common mode is going to be equal to 0.01 times the voltage input from the common mode, which we determined the voltage input from the common mode is 2 volts peak to peak as provided by part C. Therefore, the voltage output by the common mode is going to be equal to 0.02 volts peak to peak. And so that helped reduce the number. So you can see the common mode got smaller. That's what we want. It's also at the same frequency, 60 hertz BTW, but the common mode got smaller from the original 60 hertz to at 2 volts peak to peak to only 0.02 volts peak to peak at 60 hertz. So it got reduced, which is what we want from this 3 op amp instrumentation amplifier. So there you guys go. Hopefully that made more sense there for the calculations. I was overcomplicating it, so then I broke it down.
Oh, quick question. Do you guys think he curves this shit at all? Like, do you think he would curve the class or the exam or any?
Said
Is there
that
any?
he like curves it at the very end so that like it's like guaranteed that like 3 or 4 people get an A, and then he just keeps dividing it by like 10 each.
Okay, so he grades on a bell curve.
Yeah.
I think so. He explained it on the first day of class. So if you rewatch the lecture at the very beginning, he mentions it.
Oh, okay. Thank you.
Perfect.
This is just insane math, if you guys.
That's not even math, what we're doing.
Yeah, okay. Next one, number 4. I'll do number 4. Actually, I feel like I should do number 5 because honestly, I've been doing all designs. And then we'll wrap it up there, 5A and 5B, because I feel like those will be good ones to do. Okay.
Just curious, are you gonna also go over chapter 6, or are you just gonna like, because that's just like intervals and shit.
Okay,
so
he
I
did
feel
not
we
give
gotta-
us a handout at all, and it's just plug, I think, into the equations he gave us for those.
Yeah.
I
we should be-
honestly don't see him testing us much on it at all.
Cool. All right, then. Yeah, let's do number 5.
Okay, number 5, sketch the output voltage as a function of time in the circuits below. Okay, so let's look at part A. Okay, when I'm looking at this, identify the amp. So this one right here, inverting amp, and this one, because no, non-inverting amp, because the voltage source is connected to the positive terminal, but there is feedback also, so that's why it's a closed loop. And so We know this is a non-inverting amp here. And then our second one is going to be, let's look, to negative terminal. We have another non-inverting amp here. But if we go left to right, this is going to produce an output voltage. So there will be a voltage here. So I'm going to call it V out. Let me see. V out, and then put 1 apostrophe here for the output voltage from the first op amp. And so if we have a voltage here also at the negative terminal, we're going to have to use superposition here. And we're going to have to look at what this has on effect on the inverting amp, and then look at how the other one affects the non-inverting amp. So let's go one by one. Let's calculate the voltage output for the first amp over here. So we're going to focus on this portion over here. So let me circle it. That's what we're going to be doing. Okay. So for this one, what we are going to do is use our equation. So V out apostrophe, it's going to equal to non-inverting amp, it's 1 plus, and then RF is going to be 10K, then over RS, which is going to be 90K. And then now that we know that for the gain, the voltage inputted is 5 millivolts root mean squared. When you see root mean squared here, multiply this immediately or you're going to screw yourself over. The root mean squared to peak converter is going to be, if you look at this, continue to site, what we have right now, if we want the output voltage to be 5, I believe it is 2 rad 2, so 5 divided by 2 rad 2. I got for my value 1.76. Let me just check that real quick and tell you guys the calculation. Should be 1.76. Let me just look at the. Okay, so peak to peak voltage is equal to 2 times the square root of 2 times the RMS voltage. Here, what I just look at is, should be given, okay, here. Voltage peak to peak is equal to the voltage RMS times 2 rad 2. So here in this one where he went over it, what you guys need to know, right here, let me try fixing this, is this root mean square, just multiply this by 2 rad 2 to get the voltage peak to peak. So 2 gives us voltage peak to peak. Okay, so if we do 5 millivolts, 5 e to negative 3 by 2 rad 2, I'm going to get 14.14 millivolts. So I'm going to just write that here. 14.14 millivolts at 5 kilohertz. Okay. Got this part here. Now that I know that, and that's the peak to peak, what I need to do is I need to now plug that in here to the equation I was originally drafting. And so the voltage input here is 14.14 millivolts peak to peak. And so when we multiply that by 1 plus 10 divided by 90 is 1/9. That'd be 15.71 millivolts peak to peak. And that's at the same frequency, which is 5 kilohertz. Okay, now that we determined that as our output voltage here, I'm going to just write that 15.71 millivolts peak to peak at 5 kilohertz. Okay, we know that's going to be here coming in at this output voltage. And then we have these 2 sources. So first, I'm going to look at this one right here. So I'm going to circle it, use superposition. First determine what this one has an impact on the inverting amp. So pretend this source right here is set to 0 real quick. So let's look at that one. So 10 millivolt source. what's going to happen is the equation is going to be, it's hooked into the positive terminal, it's going to be non-inverting amp. So 1 plus RF, which is 90K divided by 10K. Luke, that's the gain multiplied by the voltage input, which is 10 millivolts at 0 hertz. That means it's DC, so you guys know. That's going to equal 1 plus 9, which would be 10. So 10 times 10 e to the negative 3. That's 100 millivolts at 0 hertz. And then for our next one, it's going to be this input of 15.71 millivolts peak to peak. And so I'm going to look at that one. So let's just have this be to 0. So let me show you guys what that look like. Hook this one up to 0. And then we're going to have this 15.71 as an actual source. And we're going to look at its effects upon this inverting amp. So for this 15.71 millivolt source, it's going to be, let's calculate it. So it's 1 plus 90K divided by 10K, and then times, oh wait, sorry, it's an inverting amp because it's only connected to those. So then it would be multiplied by the input voltage, 15.71 millivolts peak to peak at 5 kilohertz. And let's look at this. So negative 9 times 15.71 e to the negative 3. That gives me negative 141.39 millivolts peak to peak.
Ryan, quick question. Why did we switch from 5 millivolts? But I can't even read his handwriting. I don't know what comes after 5 millivolts.
Oh, that's root mean squared. And so for a visual diagram, because that helped me understand it, I saw it on a YouTube video before, so that's sort of how I could tell it. Root mean squared, look, that refers to just here. He didn't go over this yet, but it refers to basically when you have a waveform, it cuts it off at like the average. And so it cuts it off here. And so the reason I did this conversion times 2 rad 2 was because that's how you go from root mean squared to peak. So work in something we can know how to actually show.
But since you didn't go over that, most likely on the exam we'd have something that's peak to peak, right?
Yeah, I just did it in case so you guys know the conversions to rad 2.
Dope.
Just at least you gain the skill. You're going to have to use that in future classes.
Yeah.
Okay. Now that I went over that superposition, remember, add the contribution of each. So this is what our amplifier is going to see at the output. And so then we have a DC here, and we also have an AC. So this is going to be a little confusing. So let me just show you guys a visual diagram real quick on how each of these are going to appear. Because that will be a good one. So let me real quick look at how I drew it for myself. Okay. So for the diagram, what I want and what probably he'll want to see as well. Okay, this one's 100 millivolts at 0 hertz. So it's just going to stay right here. So for this blue one here, it's going to stay right here at 100 millivolts. This one right here is going to be peak to peak. So we know divide by 2, it's going to be 141.39 millivolts divided by 2. It's going to be 70.695 millivolts. So what we can do for this one is we can show you guys, it looks like it starts negative there by the negative sign in front. So it goes like something like this. And so that's what the second output would look like. And so here is negative 70.695. So I'm just going to put negative 70 right for now, and then 70 up here. And then we need to show the combination of these two. And so you're probably like, how in the world am I going to make a combination from this? It's not as bad as it seems because you just add the AC to this DC. So the DC one is the straight line and the AC one's the alternating current. So just add them together. So 100 minus 70, you'll see once it starts out, it's going to look something like this. So it's going to go down like to like the 30 range. Then 100 plus 70 is going to go up to like the 170 range. And then it's going to go down back to this 30, and then it's going to go back up. Oh, should be more balanced between the two sides. It's going to look like that. You're basically shifting it up to that 100 for the middle line. And the reason is the simple way is you just take the DC and just add this alternating current, alternating voltage wave to it, the AC waveform to this, and then that's how you get the combination of the two. So this is what your output waveform should be. It should go from, then if you combine the two values, because remember this one, like I told you guys, it goes negative 70 and 70, this one right here. So 100 millivolts minus 70 is going to be 30 millivolts at the low. So I'm just going to write 30 millivolts at the low. And then at the high, it's going to be 70 plus this 100 millivolts. So it's going to be 170 millivolts. Okay. So that's going to be the range of your V output. So you guys know it's going to be between these two. Hopefully that makes sense, how your V output is between that range. And now that we determined the V output, we're going to do part B. So we found the output voltage for this one. And so that part B is going to be 1 millivolt peak to peak at 60 hertz, or sorry, at 100 hertz. Oh, sorry, I just forgot to do the, on this last one, let me see. I just forgot to do the period. The period's going to be the original. So 1/5 kilohertz is going to be the original. And so 1/5 kilohertz for your period for that sine wave is going to be at 200 microseconds. So every 200 microseconds, there's going to be one complete sine wave. Okay, let's do part B. Part B is easier. Okay, so part B, you're going to analyze the contribution from this one, and then you're going to analyze the contribution from this one. Here we go, because this one luckily has just one voltage source for this entire circuit. This one, it's going to be, let's look. Okay, I remember this. If you guys recall, this is just a voltage follower circuit. And so V in is going to equal V out, and it ignores this resistor right before it. If you look at the diagram of the voltage follower, let's go here. See how it's hooked back to a negative terminal. All these op amps have high input resistance, so any value of resistor in front of it is not going to matter. The output voltage is going to equal to the input voltage. So right here, what the output voltage is going to be is this 1 volt peak to peak at 100 hertz. That resistor does not matter because the op amp has such high input resistance at each of its terminals, so there's no current flowing to any the positive or negative terminal. Okay, now that we know that source, we can basically look at the second one, and we notice that this is an inverting amp with that source because we have 0 volts at the positive terminal and we have a 1 volt peak to peak at the negative terminal. Okay, using our equation, V output is going to be equal to negative 150K ohms divided by 10K ohms. So that's our gain. And then the voltage input is 1 volt peak to peak. Okay, and that's going to be at that 100 hertz. Okay, we know our voltage output is going to be equal to negative 15 times 1. That's going to be negative 15 volts peak to peak. That makes sense. It's an inverting amp. So you guys know, and it's also a gain of 15. So that's why it's negative 15 volts peak to peak. And so that's going to be 7.5 down, 7.5 up. So when we sketch the output voltage waveform, it's going to be negative 7.5, 7.5, negative 7.5. And so we know the period here, it's going to be 1 over the frequency. So 1 divided by 100, that gives me 0.01 seconds. So 0.01, and this is time in seconds. And then for my y-axis, this is going to be up to 7.5, because peak to peak, divide that by 2, and negative 7.5. Okay, that's how we got those values there. And that is how you do 5A and 5B. Okay, hopefully that helped out with the 3-hour and 10-minute review session. I will stop the recording real quick.